Good evening, everyone. We are delighted to welcome you all to the day 5 of 6-day International Faculty Development Program on Smart Biomedical and Sustainable Electronic Systems, AI, IoT, and Green Technologies, organized by the Department of Electronics and Communication Engineering, CIMAT. We hope today's session will be as enriching and inspiring as those of the previous day. It is my great pleasure to introduce our esteemed resource person for today's session, Dr. K. Saravanan, Associate Professor in the Department of Computer Science and Engineering at the College of Engineering, Anna University, Chennai. He also serves as the Deputy Director of the Center for University Industry Collaboration at Anna University. He holds an ME in software engineering and a PhD in computer science and engineering. His areas of expertise include cloud computing, software engineering, the Internet of Things, and smart cities. He has published numerous research papers in international journals and conferences, authored several book chapters, and edited books with international publishers. He has also undertaken consultancy projects for smart city initiatives and serves as a reviewer for reputed journals including Elsevier and IEEE. In addition, he has conducted workshops in collaboration with IIT Bombay and IIT Kharagpur and has delivered over 100 guest lectures at various seminars, conferences, and workshops. We are delighted to have such a distinguished academician and researcher with us today. I'm sure his session will be both insightful and enriching for all of us. With great pleasure, I now invite Dr. K. Saravanan to deliver today's session.
Uh, Good evening, everyone. So, good evening, participants. There is a pleasure to deliver these sessions for today. So, let me share my screen.
Yes, sir. You can share.
Yeah. Hope you can able to see the screen, right?
Yes, sir. It's clear. Visible.
Yes, sir.
Okay, great. Thank you. So today evening, we are going to discuss about the artificial intelligence that is impact in the communications as well as in the healthcare domain. So both are very important domains. And also the AI impacted in many domains like insurance, banking, smart cities, educations, all such kind of there is a domains. Its impact is very huge. And also, right, it's going to impact in there is a features as well, right? So we have AI and the concepts with deep learning and generative AI now come with kind of agentic AI. That is a process, right? It's also started with. So now this topic is about right AI, how it is revolutioning in 5G and 6G communications, and what are the research challenges and its opportunities. So as I said, right, myself, Dr. Saravanan, I'm working as associate professor in the Department of Computer Science Engineering in CUG campus, Anna University, Chennai. So we are the current users of the 5G, right? We know what it impacts. So in the mobile communication network, so we are the ultimate there is a user of it. So previously we used to get like 1 GB of data. Now it's all about a 10 Gbps, and we are enjoying there is a speed of this internet. There is a connectivity, so it's going to be seamless. Right, the video connections on the move. Right, you can watch this kind of literature in a real time mode. It's right. It's a we have to thank the 5G. There is a communication though, right? Because of it, right? So wherever you are, right, you are on the bus or you are on the train, right? You can still watch this. There is a presentations on the move. So 5G is the fifth generations of wireless technology, and we are at to there is a receiver, there is a 6G as well, right? Maybe in the year 2030 or something. Okay. So it provides high speed data and we have a low latency, but also massive, there is a connectivity. So uh, so not only right there is a systems or there is a human so connecting to the internet, it's all about right that of IoT, there is a devices, right? So IoT devices, any devices that is connected to the there is internet, right? So a lot of there is a CCTV cameras and sensors, right? They sense a lot of there is a data and they are connecting to the internet with the help of there is a 5G. So all this there is a data we are receiving in the there is a real time, there is a mode and it is also getting processed and also right it can be there is a predict and also used for there is prediction with the help of there is a machine learning platform. That's what right. So have to there is a thank the 5G there is a network. So we have enhanced mobile broadband, so ultra reliable, low latency communications, and massive machine type communications. So it's about M2M communications we are talking about, right? So it's not only right that is human to there is a machine, so it's also right machine to machine communications. So maybe the drone to drone communications, right? We are using drones heavily in the war. There is a time given recently in the Indo-Pakistan war, right? So we use the right. There is a drones, there is a heavily, right? So which means we extensively using there is IoT based there is a devices in all the environments. So if we are using in the medical, there is called IoMT devices, right? Internet of medical things. If you are using these drones, then it is called Internet of there is a drones. Right? So in agriculture, we are using right in Internet of there is agriculture, there is a things. So this means every domains, right? We have to there is a categorize these IoT devices. And these IoT devices basically capturing the video data as well as they sense with a lot of uh, sensors actually. There are various type of there is a sensors for each for every domain, right? We have a different type of sensors as well. So the 5G right capitalize those kind of there is a communication there is a model. So what are the applications? So for currently that we are there is using. So network optimizations. So how the AI is used in there is a 5G network that we are talking about. So 5G is a communication technology and AI, right? So which is used for there is a prediction or for analyzing there is a data. Right? So we have this 5G communication data, right? Then what is there is a purpose of using AI thing in the 5G communication network. AI algorithms improve the performance of the 5G networks. So there is a 5G network, so how to make it more optimized? So because the 5G network is about bandwidth, resource allocation. So we have the network that should be sliced and spectrum has to be managed, right? So with the help of the AI algorithms, so we can able to utilize or better optimize there is a 5G network also. So resource allocations like routers, switches, and networks, and everything gateways, any device, right? So with the help of this, right, we can able to optimize it and network slice. So how you uh, distribute there is a network environment because everything is comes under the kind of there is a service now, right? So we can call it as a software as a service, platform as a service, right? Infrastructure as a service, then, right? Even the network, right? The communication network can also be given as a kind of there is a service, then, right? So maybe the underlying the infrastructure would be the physical, but whereas how we can able to slice it and give it to the there is a user, right? That comes with the AI algorithm, right? Then comes to there is a traffic management. They predicts the network traffic patterns and allocate the resource dynamically, right? So we would expect a very huge demand. So when whatever the net, because network is the backbone for anything. So we have something like there's content management systems. So YouTube or a Facebook, right, or anything, right? So people extensively using these kind of there is a content network, right? Content management systems. So these content should be provisioned and they should be allocated in a very dynamic and real time there is a manner, right? So how you have to manage these kind of there is a huge there is a traffic then. So there could be there is a peak traffic and there is no traffic at all. So though so both the end right we have to there is a manage them. So there is a huge traffic at the particular period of point of time, right? The peak traffic then, right? How the AI will predict it, right? Then how it will increase the resources ability then. Right? So if you have a huge number of resources, then you can be able to manage the traffic very effectively. And also if it reduce the congestion and improve the user experience as well. So that's where the AI play the important role in there is a traffic, there is a management. It's not about traffic management when it comes to in the present level. It should also have to predict there is a traffic and there is a future. Okay. And the next level is going to be predictive maintenance. So the predictive maintenance, what it means. So all the devices tend to there is a failure, right? Even when it comes to there is a large industries, we are employing the very huge number of there is a sensors and equipments and so on, right? By applying the sensor, you could able to monitor the current performance of these devices as well as its past performance, right? So now we have the data about the past performance of a particular motor. So or also we can say there is any equipment, right? So from previously, right, any equipment, right, it tend to reduce its performance over the years, right? The pattern we have to there is identify, and from the pattern we would able to say that right when will be that there is a downtime or the failure yet to come for the particular there is a device. So if we can able to there is predict, we could able to easily replace the particular there is a device in a very easy manner, right? That's about kind of there is predictive maintenance, right? So for all these things, we need a huge amounts of there is a data from the 5G communications. So based on the logs, right, based on the current network traffic, right, we could able to gather the data and also from the sensors attached with the 5G equipments then. Right? So there are a lot of the sensors that we can attach with the 5G sensor, 5G communication network, right, through which we could able to do the wonders. So this is the evolutions of wireless networks. So we have a 3G right from the right 2000, which means the 21st century, the start of the 21st century. So the communication networks are getting right boom. So we have 2000 3G networks and 4G, 5G, and 2030, right? It's evolution support that is a 6G. When it comes to 6G, it's about the haptic internet, fully automated. There is a training with the help of SDN and industrial internet. So all the industries are attached with there is IoT devices that we call IIoT, right? Industrial IoT. So because so it's not about the automations comes with right only there is a sensor network or maybe the personal devices. The entire this industry is also getting automated. The workflow is automated, and also the devices is getting connected with the internet. Then we have IoT devices. So and also distributed intelligence. So the intelligence, right? It's not only for a particular industries, right? So it is also connected with all other there is industries in line with. So the traditional network architectures comes with data plane and control plane. So which is are not separated, right? So which is comes with a single plane then. So there is no programmability here. So you have a data plane and control plane, right? There is a single, then there is a lot of there is a traffic in place, so you can't able to there is a control over it, right? But when it comes to SDN, right, so there is another technology, right, software defined networks. So you shall have a separate plane for data and separate plane for there is a control, right? So the control devices will sit on top of your the data plane and it will manage the network traffic very effectively. So with the help of uh, the 5G and the 6G networks, and have something called network function virtualization, because we are talking about right anything as a there is a service, network as a services, right? So we have underlying the huge network there is a services that should be sliced, and then so on the network should be there is a sliced and should be given to the users, multiple users, concurrent users basically, right? How we can do that? Only with the help of the virtualization. The virtualization concept evolved from this, right? Yeah, it is a backbone of there is a cloud computing, right? So the same kind of network virtualizations happens for the 5G and then 6G communications as well. So now we are utilizing the smart cities with the help of the AI algorithms. So AI analyzes the real-time data from millions of connected sensors to manage the traffic, energy consumption, and public safety efficiency. So there are various use cases in a smart city, because if you say smart cities, again, it's a generalized right the way of right specifying the applications. In a smart city, we have a solid state management and then the wastewater management, and we have street lights, which is we have smart street lights and smart water management, and then CCTV surveillance, which is ITS, intelligent traffic management systems, right? And then we have uh, yes, energy management, consumptions, how much energy is consumed, right? So we have a huge number of, and also the healthcare applications, huge number of potential applications, and these applications are getting connected to give a holistic smart city environment. Right? So we'll get the energy data from which from one of the applications, right? And also smart street light data, and also there is a water data, and also we have tax collection data, you have a grievance data, right? So everything will be getting into a single, there is a smart cities system, which is called as a integrated, right, control, command and control center. We, right, there is a, they call it as an ICCC, integrated command and control center, in which, right, we can make decision, the authorities like city corporations, commissioner, or maybe the authorities will make a quick decisions about anything, right? Any abnormalities that comes with it. Okay. Then comes with autonomous vehicles, right? So the future is going to be autonomous. There is a vehicles, right? So there is no drivers involved with, right? So if the network or maybe the road infrastructure is built in a proper way, then there is a possibility of, right, the autonomous vehicle. Probably, right, in all the there is a Western countries, right? They come up with autonomous vehicles, but it may take time in India. But definitely, right, the autonomous vehicles is also potential use case for there is a 5G and also for the there is a 6G. Right. So now we can uh, definitely implement the autonomous vehicles, but it's because of the what we call the disciplines of the people itself, and because of the lack of the civil road infrastructure is still lagging, right, in India. So that is the reason, right, we can't be able to implement, right? Because the technology wise, right, the autonomous vehicles, right, is simply is mature now. Whereas the civil infrastructure, right, we didn't get through right now. So once it is done, right, then we can easily implement the autonomous vehicles environment in India as well, right? Because so any technology, right? So if you want to, there is an implement, right? It's just kind of there is an ecosystem, right? So there is an allied technology should also be matured enough so that we could be able to use the mature there is a technology, right? So maybe in there is a past there is a there is 3 decades before, right, in cinemas, right? So the people imagined about or they can talk about the real time what do you call there is a speech, right? So I can sit here whereas, right, I can through the mirror I can able to see the other persons that is sitting in somewhere. It's a kind of there is a futuristic there is a dream that was made in the there is a cinemas, there is a 3 decades before. Now it is in real time because, right, the dream is something, right, happens just before, but there is no technology involved at that point of time. Now we have kind of there is a technology to make it in a real time, right? So one person sitting in the US and one person sitting in India, right? They can see it in a real time because we have there is a 5G. Because of this 5G, right? In a real time manner, you can see this kind of there is a person. But actually, there is a future technology called there is a 6G comes in, right? Which will bring there is a more effect then. It's not about only the two-dimensional picture of a person's in a real time. We are going to talk about the three-dimensional view of the person. So it's going to be a real-time immersive experience. How the real person is sitting next to me, right? So that's the kind of experience will bring with the help of there is a 5G. So it's kind of there is holomorphic or holographic, there is images, right? With the help of this, right, we will build a 3D version of there is a person's in a real-time manner, right? Just sitting near to you. It's not real, but still it's give you the real-time immersive experience too. Okay. Then comes with remote healthcare. Anyway, so the healthcare applications we'll talk in the there is a separate topic, right? In the next there is a session. And so AI enables real-time diagnosis and surgery, right? So we have robotic surgery currently that is happening and real-time diagnosis with the help of also such kind of easier records. We will be able to diagnose that there is a patient records as well. So I'll give there is a pause here. So if you have any questions, I can reply to you. If there are no questions, we can continue. Okay, so I will continue that. So AI-driven 5G network architectures, right? So what it brings to the network architecture then, right? So about there is a cloud computing, right, which is the backbone of any internet, right now, right? Because uh, we use anything as a kind of there is a services, right? So all such applications are built using the cloud services. And there is a variations of cloud computing as well. There is something called fog and edge computing. So what it means, right? So where the physical devices are there is a locator, right? How because I want to use the services, but if it is processed in a very distinct, there is a place, right, in a cloud servers, something called we call as a data center, right? So in a data center, so definitely it may take time, though it is there is a real time. So cloud computing, right? The physical server located in the data center, right? So there is a latency. So in which, right? So that's why the 5G there is a solve. Even the 5G solves also it takes time. The people want it make it more and more in a real time manner, right? Then you have to bring such kind of there is a data center or devices very closer to the users or very closer to the there is a processing part, right? Then comes with there is a fog and the edge computing as well. So what is meant by there is edge computing then? So edge and cloud, right? So here we can make it as a very distinct. So edge computing, right? You move the processing of the data very nearer to the devices, right? Which means, right, the data are generated from the devices, and this data has to be moved to the there is a cloud, right? So what happens if I can able to process the data very near to the there is a devices as well, right? That's the concept of the edge computing as well. So why we need edge computing? Because I need reduced latency. I need the data processing closer to the resources as well. And of course, it's not, we can't say that, right? So all the applications, either edge computing or a cloud computing or a fog computing, right? It could be like partially an application's data can be processed through edge computing, and another part of data can be processed as a fog, and another process of the data could be that it's a cloud computing, right? So because of the need of kind of this application, I have very large enterprise applications. I have some sensitive applications and non-sensitive. So what we call the sensitive data and non-sensitive data as well, right? So the sensitive data, right? I don't want to disclose the data to any third party. There is a cloud servers. So for which, right, I can use the edge computing then. So I can process the data within this, right, the edge, there is a servers, which is placed very nearer to the there is device itself. And what's the cost involved, right? You have to employ more devices, more backup devices then, because the cloud will have the proper package, proper applications factors, right? And also to have proper, there is a security mechanism. But if you want to bring the cloud to the nearer to the device, something called edge computing, then you have to pay the cost for it, right? So you have to employ with the more backup devices as well, right? So what is the benefit I will give, right? I don't want to send the data to the cloud because I can keep the data within my premise with the help of the edge servers. And in between, right, we have something called that is a fog computing as well, right? So the fog computing, right? So it's kind of intermediate nodes. It's not like there's a cloud. It's not like there is edge. So just reside right in between. So that's the way, right? The computing evolves. Hope you know, right, the difference between the network architecture, right? This is the way it looks like, right? So there are sensors, right? And there are actuators, there are CCTV cameras, right? There are large number of there is devices, right? So that generates large amount of data, right? So which we call as kind of the edge devices, and the edge server is located within the edge devices itself, right? Then we have to move this data to the fog networks, and then also we have to move the data to this cloud data center as well. Typically, the data center, the physical place of this cloud, right? So when it comes to the edge devices, it's going to be there is a millions, and when it comes to there is fog networks, it is going to be sorry, it's going to be from billion to million, and from million to there is a thousands, right? It's getting reduced. And if you know this kind of the difference, it's very easy to characterize, right? So based on this, the metrics, what is the latency? So what is the scalability? How much the distance, right? So when you say the distance, right, the cloud is very far from the edge and far, it network close to the edge, and right. So when it comes to the distance or edge device, it is just placed at the edge itself. We have a huge number of edge devices. The edge servers is just located very near to the edge devices itself. Okay. So what about the computing power? When it comes to cloud, it is very high because, right, so it computes and everything. Whereas the fog and then edge, right? So it's going to be, there is a very limited because we can't have large number of there is a computing power to the there is edge computing itself, because mostly the edge is kind of there is a battery enabled, there is devices, right, through which you will do some sort of processing. So mostly these kind of there is a processing look like a aggregation or filtering basically, right? You will do the filtering as well as aggregation functions here, the edge devices, because you want to filter, right? So what data to be sent to cloud and what data to be eliminated in the edge itself, right? I will give you an examples as well, right? Because, for example, right, you have a thousand sensor in place, right? In a edge, right? In a typical applications environment, and most of the time, out of this thousand sensors, right, only the 50 sensors, right, will generate the meaningful data. So remaining, right, 9,000, not 9,000, 900, and there is a 50 sensor, right? Will always generate the null data, right? So whenever if something happens, right, then only it will generate the data, right? So something like if we say there is a CCTV, right, the footages, right, if from some persons there is a ghost, then only the detection comes, right? So the obstacle there is a comes. Or maybe some environment, there is a sensor, right? So if there is some variation in the sensor, right, then only they detect, right? If there is a variations in the environment, or maybe there is a CO2 or something, right? So if there are any variations comes, then it will detect and the sensor data has to be moved to the there is a cloud. If there are no variations, right, then the point is something like, right, is going to be there is the same data which is comes, so we can consider as a null data of it, right? So there is a null data. So what's the point to send the data to the cloud, right? So only if the variation comes of uh there is a potential value in the edge devices or in the sensor, then you can process into the cloud. Otherwise, right, just filter it out, right? So whatever the sensor, right, only the 50 sensor have the potential, there is a values, and the remaining 950 sensors. And I'm talking about the 950 and then 50 dynamically vary, right? Are the every there is a 20 minutes or a 10 minutes or the typical there is a frequency something, right? The 50 sensor I'm talking about, right? So it's also going to dynamically there is a vary, right? It's not about the 1, 2, 3, 4, 5, 6, 7. So one time it's going to be 1 to 50, and another time it's going to be right 2, 10, 15, 35 or something, right? So dynamically, right? There are variation happens, but I don't want to send all kind of there is a sensor data to the cloud. So what are the sensors having the fluctuations? So those sensor data has to, but in order to do that, right, I have to do some sort of processing at the edge server end, right? That kind of aggregations and filtering can happen in the edge computing. That's why. That's why, right, we have to employ the edge server. That will save. There is a lot of data, right? Traffic, right? In the there is a cloud server end. And what about interoperability? So when it comes to cloud, because it has to manage the different type of devices, right? Interoperability. When you say this interoperability, how you manage the different vendors, how you manage the different framework, how you manage the different devices and everything, right? So interoperability will manage and everything. So when it comes to cloud, so it is going to be high. When it comes to edge, right? It's going to be a particular vendor based, right, the network, the definitely the interoperability is low, right? So similarly, we get able to identify a lot of there is a characteristic. How about the scalability, right? Cloud is definitely this scalable because that's the basic characteristics of the cloud, right? Whereas when it comes to there is edge, right? Because this edge server is very limited, so it's very hard to there is a scale. Okay. So when it comes to there is a latency, so edge provides a very lowest there is a latency, but when it comes to there is a cloud, because it's located far away, right, from the devices, then definitely, right, its latency is there is a high. So depends on my application requirements, I had to finalize, right, what kind of model I had to go with, right? Either completely cloud or completely edge, or I have a combination of cloud and fog and then edge computing. There is a model. So now comes with there is a 6G communications now, so which is going to be the futuristic, right, the networks model, right? So it's upcoming the sixth generation of wireless technology, and it's expected to go beyond 5G. So what it means, right? So definitely, right, we see there is 6G and then 5G. What's the difference? So you have more, right? There is a speed, right? The tactile interactions, allow real-time touch interactions over long distances. So revolutioning the areas like remote surgeries and virtual reality. So it's not like we are going to download anything now, right? It's all going to be something like in real time, right? In order to download anything, right, you can, right, make it in a real time mode. You can, right, the data will be there as it is, right? But whereas with the help of there is a 6G network, right, you can seamlessly, right, visualize those kind of there is a data in a real time. There is a, and we talk about it, the holographic communication, which I said, right? It's a 3D holograms for immersive experience in communication and entertainment. So the entertainment industry, right, which is going to widely going to use. Already there is a lot of there is a country started using the 3D holograms. So they're making the immersive experience of the movie scenes and something, right? So you will get the real time, right? There is a picnic, right? There were a lot of places they used it, right? The 3D hologram image of anything, right? The movie or particular there is a scene or a particular Jew environment, right? Anything we can make it in the 3D hologram environment. And quantum computing, right? So the quantum computing is also one of the technology, right, which will make it more versatile environment. So integration of with the quantum technologies for enhanced data security that will make more faster and more right uh, very way of ultra faster there is a processing of there is a data. So when it comes to there is a quantum computing in order to process the quantum particles, so we need such kind of the 6G communication because the quantum processor will make it a very quick path for fast processing and which will brings the data to the users. That's why we need a 6G communication then. And AI native infrastructures. So it's not about right. AI is something away from the communication network. It is inbuilt with the 6G network. So 6G is built with the AI. Right? So AI networks is built with the 6G infrastructures at its core, allowing the autonomous management and optimization of the resident networks, which means, right, all kind of the resident networks, the 6G networks are built with the 6G for better optimization and better traffic managements. So these are all envision use cases. So when we bring AI into the 6G communications networks. So it's a terahertz communications and AR and VR, which will bring the real time, right, the holographic experience in a 3D mode and the quantum communications, right? So it's about not the quantum technology, it's all about the quantum communications and blockchain. So which is also one of the, right, there is a technology, but it has to wait for, right, the 6G communication in place so that, right, you can able to identify more number of use cases with the help of this blockchain technology and mobile edge computing. So the edge computing, so not only with the help of this web-based applications, right? So all sort of mobile devices is also equipped with the mobile edge as well, right? So we will do the processing. Individual mobile devices will also have the ability to process the data within the mobile device itself. And of course, unmanned aerial vehicles, right? Which means UAV vehicles, drones will come in space, and M2M communications, drone to drone communications will take in place. But not to do that, right? So, for example, sending the video from the drone to another drone in a real time mode, right? I will also give the use case of, right, in a typical there is a war environment, right? The drones are identified with the help of our machines, right? So we can be able to identify that there is drone where it is coming, and we can able to demolish the war or demolish the drones, right, before it comes to reach the right, the enemies that is a place, right? So we have the defending mechanisms in place, right? So, but if happens, so what is the purpose of that is sending the drones? Because the drones went before reaching it, right? So we have the defending mechanisms, we should add in the drones. But the drone has to send a message to its followers, right? Saying that, right? So you have to take an alternative way, right? So that you can be able to take right diversions of the defending mechanism, right? How? Because for which, right, we need such kind of, right, the real-time communications models between the drones. But this imagine, right, assume that, right, so these drones are in uh, been a satellite, there is a space, there are no kind of, there is a communication mode is there, right? But still, so they have to communicate very effectively from one drone, not to another drone, to all other drones who are going to be, there is a followers. So there are lot of, there is a challenges in between, but with the help of this 6G technology, right, we can able to, there is a do it. Of course, all this, right, we have to use the artificial intelligence, there is a technology thing, right? IRS technologies, optical wireless, right? So all this potential applications get benefited with the help of AI inbuilt with the 6G communications. So the vision of AI, and there is a future 6G networks. So HAA and AI for wireless networks, and AI embedded applications, and self-definable networks. Right. So networks, it's not configured by the humans or by the systems. The network themselves more optimistic and more dynamically, they could be able to self-configure themselves. That is called, right, the self-definable, there is a networks. So the requirements for 6G, then intelligent connectivity. So it's going to be wisdom connections in the network, and AI assisted massive connectivity. And there is something called deep connectivity. It's a deep sensing for cloud, edge, and computing devices. So based on that, there's a data, right? What is to be there is a done. I have to go with a cloud based or edge based or computing based. And ubiquitous connectivity. It's not about, right. So only in a single place. It's all about, because when it comes to this internet, it's all about ubiquitous. It's a pervasive, right? So then similarly, right, the connectivity also, right, is going to be there is ubiquitous, which means all the devices are connected to the closures, all connected can be communicated to the closure node, right? So anything, any device can able to communicate any devices, right, in a perfect manner. But still, we have a lot of issues. We'll have, there is a privacy and then security issues that can be, that should be taken care, right? Right, by the, there is a systems, but still, right, the technology provides such kind of, there is ubiquitous, there is a connectivity then. And holographic connectivity, it is kind of 3D view of the devices in a immersive way of experiencing, right? Anything experiencing the anything. It could be an object or it could be a human, right? Anything you could be able to experience in a real time. So, yeah, applications in 6G. So, what are the type of applications in 6G? So, with the help of this tactile internet, right? So, AI helps process haptic feedback in a real time, enabling users to interact with the virtual objects as they are, there is in a physical mode, right? So we could able to connect the virtual objects in, like in a real time, there is physical mode. And AI augmented real time decision making because of its, right, the decision making, right, because of this critical applications, we could make a decision making in a very quicker manner, right? Imagine in a real-time healthcare and autonomous driving, right? So the data should be more and more, there is a peak and we have to make a decision. So we have autonomous driving car, right? So if it is in place, so it has to take a decision of whether it is a left or right, like a human brain, right? It has to make a decision very, very quickly, right? It's less than, there is a milliseconds, we have to arrange the decision and you have to take a decision. And also real time, there is healthcare. So based on the um, right, the real time data of there is a human, right? We have to take a decision. So what to be done to the, there is a persons. This all happens with the help of, there is a human now, right? With the help of this sensor now, right? We have the continuous monitoring of these devices like cars or maybe the human or with the help of wearable sensor, right? And we could be able to give this data to the people and we have to give that decision making in a very, very quicker manner. They could able to make a decisions. Ultimately, the final decisions will be taken by the human, but whereas, right, but the real-time decision making that can be with the help of the AI, right, we can able to do it very quickly. And holographic communication, that is what we talk about, right? AI helps in rendering the real-time holograms with ultra-low latency for next-gen communications and also the entertainment industry. Entertainment and cinema industries are going to get benefit of it. So, so what about the network science, right? The 6G network science, right? So we have physical layers, of course, we have MAC layer, we have different layers, right, of right, the network management. So if we employ the AI, right, in a different layers of the communication networks, so what is the benefit of it? Right? They bring the AI into the core of the 6G networks, right? For example, right, AI for physical layer, the physical layers talk about it, and this is the underlying layer of right any kind of network. So we talk about the OS layer. This is a bottom up layer which will take care of the physical devices which carry the data itself. Right. So the channel encoding and decoding, AI assisted positioning and sensing and localizations and channel estimations and equalizations, AI compatible edge devices. It's right. It could be a router, it could be a switch, right? So anything, right, we have to employ that. There is AI networks that will make more optimization, more routing algorithms. Then, no, again, the routing will happens in the MAC layer or network layer, right? So then AI for operation and management, so dynamic network orchestrations. So which network to be used more effectively? It's not going to be a single, there is a network or a dynamic network. We have to make it more dynamic network because of the congestions, because of the content management systems that we are in place, and more dynamic slice management, how you slice the network, how you slice there is a spectrum, how you slice there is a frequency, right? Frequency of there is an network. And control and policy enforcement, right? So we have the control plan and data plan. How you control this, there is a network with the help of the SDN, right? So more self-aware, right? SDN networks will be formed, right? So with the help of this AI networks and critical network managements and measurements and monitoring and security enhancement system. And we have for higher layers, right? So we have AI assisted brokering mechanisms, slice admissions control, and slice scheduling, and handover management. Because typically, right, in AI network, we have a different types of there is a cells in place, right? So how handover now still the handover will be that there is a problem. So that's why we have the drop off. There is a cause. So drop off networks in place, right? So when it comes to right the 6G networks, the handover mechanisms will be more easily so that right. So there is no drop off calls or drop off internet will be in place in a 6G networks. So dynamic scheduling of resource, adaptive power control, and inference management. So there are a lot of interference, right? There are a lot of noises over there is network. That is a very common thing. But when it comes to there is a 6G network, right? So this can be managed very effectively in a better management level, right? That's why right we'll have a very less interference of there is an answer system. So again, I make there is a pause here. So if I have any doubts, you can still ask. Okay. So we'll continue. So here powered use cases, right? So immersive experience, realistic environment interactions in real time, are smart homes, right? So again, the smart homes is all based on this IoT devices, smart homes and the smart cities, right? So since we have various IoT devices that is connected to the internet with the help of this 6G, it will bring more experiences. So AI controls and optimize home automation systems, entire automations, learning user preferences to improve the convenience and the energy experience. The feedback loop is more dynamic than right, that which means right. So whatever right the user experience, the feedback is more mature, and it will get the feedback and it will immediately right improve the systems for the betterment of the user convenience, right? So the loop is right very dynamic, and the loop is very fast then, right? So the reverse engineering happens within there is a second. And of course, the autonomous there is systems, autonomous vehicles, and there is called V2X networks, right? Vehicle to vehicle, vehicle to network, and vehicle to infrastructure, right? So we got any vehicle to there is intermediate network, the road infrastructure, and then more autonomous vehicles will comes in place, right? And more autonomous, there is robots and drones will also be in place in industrial, healthcare, and delivery applications. Not the drones we talk about only in the wartime. So it is used in medicine improvement, right? It could be used in delivery of any application, right? In healthcare, right? In what do you call logistic, right? In a better logistic, right? With the help of more autonomous system, the drone will be used for better delivering of there is a goods and something, right? So we will experience better lifestyles basically. And AI-driven SXG network architectures. It's a quantum computing integrations. So AI and quantum, when it is mixed together with the help of this 6G input, right? So we have three technologies now. One is there's a quantum is evolving, right? So that will make a decision very, there is a conflict because with the help of this quantum, there is a particles. Then there is a communication technology like there is a 6G and this AI. So AI is also, or AI already have the matured, there is a version now. So with the help of agentic AI, right, the maturity AI network ground, right, that is again connected with all kind of other, there is a technology. So we'll get the immediate, there is a benefit of it, right? The quantum AI plus 6G, there is a network, very fast, right? Agility based, there is a decision making, and we'll have that very real. So when it comes to there is a real time, right? It's immediate, there is a real-time applications now. So all sort of complex real-time applications will get benefit of the AI-based application. And neuromorphic computing, that's what is maybe neuromorphic computing. So any technology is going to mimic the human brain, but it cannot able to make right very real time the decision making when compared to there is a human. So but the neuromorphic computing, right? So with the help of AI and the 6G networks, right? So we can able to right make the 100% matching of right the human brain. So there is about right the neuromorphic, there is a computing term. So with the help of there is neuromorphic chips that mimic the human brain can process the sensory data in a very real time for smarter and faster decision there is a making. And cognitive radio. So AI-powered cognitive radio systems optimize the use of spectrum allocations, scheduling in a more dynamic manner that ensure efficient and fair bandwidth allocations to all the concurrent users. Then. So there will be more concurrent users. There are more number of concurrent devices. There is growing very rapidly, which means more exponential manner, right? So whatever the devices that you are connected to the internet, so that will be growing exponentially in the future number of the result in future, right? So we have very large number of billions IoT devices that is connected to the internet. Then we have to make it more dynamic allocation of the network. There is a slices as well. That happens with the help of the that is 6G networks and 6G and ambient intelligence. So we have metaverse, we have extended reality, right? Augmented reality, right? And also virtual reality and extended reality to the real-time users and holographic communications and digital twins. We have predictive maintenance because most of the industries, right, will have its digital twin because of they can able to monitor, they can able to visualize the systems in a real time. There is a manner then, and we have a real time tactile internet as well, right? And it's not about the human machine interactions. We have smart society, smart city, smart factory, and smart home applications and anything that is connected to the internet, anything that benefit of right AI based applications, right? Then we can call this make it as there is a small, right? And vehicle systems, more autonomous systems and more drones, aerial vehicle systems, or more robotics that is systems in healthcare or handling of the sensitive devices, right? We can go with the kind of this robotic systems system. So the seamless device collaborations, MPM communication, device to device communications, drone to drone communications, agree systems to real-time users that can happens with the help of, right, with the help of the internet system. The smart spaces, AI uses context-aware algorithms to make a smart decisions about energy usage, security, and connectivity without any human intervention. That is what, right? The human interventions is going to be very limited because these machines, right, going to mimic with the help of neuromorphic computing So they are going to make a decision, the self decisions, and these decisions will always be very, very closer to there is a human. Then we will have a more autonomous, there is a system sync, there is a placement. So I'm just running two YouTube videos here for time.
Over 100 pounds of metric in a second. They're saying that it will be able to support 10 times the number of devices and that it will be.
Can you able to listen this audio and video? Yes. Put in a chat message. Can you able to listen this video? Yes. When someone can unmute and say, can you able to?
Next time it's reliable. Today we're exploring the powerful trio of artificial intelligence, machine learning, and sixth generation networks. Together, they're set to revolutionize our digital world. We'll uncover the key changes and improvements that we can expect to see as these technologies evolve and work together. We'll also look at the important parts that make up the 6G network and how they function. And that's not all. We'll also unveil the 7 most critical challenges and questions that researchers are looking at right now, giving us a glimpse into the future of these technologies. So, let's get started. 6G is envisioned to bring transformative changes by the next decade, significantly upgrading the existing 5G networks. It aims to achieve global coverage, higher data rates of up to 1 to 10 terabytes per second, and lower latency of less than 1 millisecond. 6G is set to operate on new and unused radio frequencies. These ultra-high frequencies, often referred to as millimeter waves, will allow 6G to transmit a lot of data at incredibly high speeds. This means faster downloads, smoother streaming, and more efficient data transfers. One of the unique features of 6G will be its ability to use wireless sensing solutions. This means 6G can adjust its frequencies based on the environment, ensuring optimal performance at all times. This adaptability will make 6G more reliable and efficient. Unlike traditional networks, 6G is expected to adopt a decentralized approach. This means data can be processed closer to where it's generated, leading to faster response times and more efficient data handling. The integration of AI and machine learning is expected to enhance network management, spectrum, and energy efficiency. 6G networks will also focus on comprehensive built-in security features, unlike previous generations. The networks will be more heterogeneous, incorporating various communication scenarios and technologies such as satellites, unmanned aerial vehicles, and high-frequency bands to meet the diverse application requirements and performance goals. Various countries and regions, including the United States, China, Japan, Russia, the European Union, South Korea, and India, are actively participating in the development of 6G technologies, aiming to be 6G ready by 2030. 6G is poised to be influenced by user demands and emerging technologies. It will incorporate dynamic spectrum allocation, network slicing, smart antenna systems, big data analytics, and high-capacity backhaul networks, among other technologies. Innovations like integrating radar and mobile technologies, energy transfer with wireless information, and sensing and communication integration will also be pivotal in 6G development. Advanced technologies such as quantum communications, terahertz communications, and optical wireless technology will play a crucial role in shaping 6G networks. AI and machine
Yeah, I'm
learning
just playing
will be
the video
instrumental
right now.
in optimizing and enhancing the 6G network. They will contribute to various aspects such as network configuration,
okay. Just a second.
optimization,
Okay.
resource allocation, and reinforcement learning.
Yeah, sure.
AI and machine learning will facilitate adaptive network functionalities, predict requirements, and performance
I will
goals.
stop and then I'll
Various
okay. I think they cannot able to stay the video. I will stop sharing and then share it right now. That's what I asked, right? So, what about right now? Can you able to see the video? Hello? Can anyone unmute and say? Can you able to watch the video?
No, sir.
What?
Video is not visible.
Okay, so it's a kind of there is a screen sharing now. No.
No.
its ability to use wireless sensing solutions,
What about now?
Video is visible.
adjust its frequencies.
Can I able to hear the sound as well?
Sound is also.
Okay. Times. This adaptability will make 6G more reliable and efficient. Unlike traditional networks, 6G is expected to adopt a decentralized approach. This means data can be processed closer to where it's generated.
Sir, not audible. Sir,
Is it not audible?
no, I cannot hear the audio.
Okay, from the start.
No, middle.
Oh.
Concerns regarding user data protection and privacy.
Yes,
Number 6,
audible.
holographic type communication, or HTC. HTC refers to a communication technology that aims to transmit holographic data, enabling a 3D and immersive communication experience. Unlike traditional 3D images or videos, HTC aims to provide a true holographic experience, allowing users to perceive the depth and various perspectives of 3D objects naturally with the naked eye. HTC has seen significant advancements, but its implementation requires extensive bandwidth, ultra-low latency, and high-precision synchronization. Number 5, multisense experience in 6G. 6G aims to revolutionize the communication landscape by transcending beyond the conventional realms of sight and sound, which predominantly characterize current communication systems. By integrating multisense experiences, such as smell and taste, 6G aspires to foster the development of innovative products and applications across various sectors, thereby enriching the overall user experience with a more immersive and multidimensional form of interaction. Number 4, digital twin. The digital twin concept is a revolutionary idea that involves crafting a precise virtual replica of a physical entity, mirroring its attributes, features, and behaviors in a digital realm. This virtual counterpart allows for real-time monitoring, analysis, and simulation, offering a powerful tool for optimization and innovation. While the concept has already captured significant interest and seen preliminary applications, it is in the era of 6G networks that the digital twin is expected to unveil its full potential. Number 3, computation-intensive AI technologies. 6G networks will likely leverage new technologies such as distributed computing resources and mobile edge devices to facilitate efficient machine learning training and inference strategies. Number 2, privacy and security. Despite advancements in quantum cryptography and physical layer security, further research is needed to ascertain their applicability in 6G networks. Additionally, privacy protection, especially during model training in machine learning and AI applications, remains a significant challenge. Number 1, extended reality or ER. 6G, with its promise of unprecedented data capacities and speed, is poised to be the catalyst that propels ER to new heights, enabling it to achieve visual qualities that rival those of conventional 2D video streaming, thus opening doors to richer and more engaging virtual experiences. If you've watched this video all the way through, we'd love to hear your thoughts. Drop a comment below to let us know you've gained some insights from the content. For more interesting topics, subscribe.
Imagine stepping into a world where the rules of reality are rewritten, where particles can be in two places.
So what are the research challenges in AI for 5G? So when you're adopting any technology, right, so that definitely will face, there is a lot of changes as well. So what are the challenges of AI in 5G and 6G? The first issue could be the scalability. because of the number of connected devices grows. So definitely the AI algorithm need to scale efficiency, need to scale the massive values of data. So the number of devices also getting increased and the amount of data that they are sending. There is going to be the massive values of data, right? So both will be there is a case. So how you solve this, right? So we have, so instead of there is a processing in a centralized, there is a place. So why can't we have a distributed AI architectures so that enable localized decision making there, right? So the concepts such like the federated learning, right? So we have machine learning and also there is a federated learning. So what is will be there is a federated learning concept. So the AI models are distributed and it is there in the local systems, like in edge computing. So we will process the data in the local. So similarly, the federated learning, which is a distributed machine learning model. So that sits in the local edge devices and it process there is AI, there is a model in local. So that's the way we could able to come up with there is a solution then. Then data security and privacy. So definitely there is a challenges with the data and security and privacy when it comes to any network. So how we can able to solve it? We have to go with more modern encryption techniques to secure the communications and privacy preserving AI models such as differential privacy and homomorphic encryptions. So those kind of encryptions model that can be used to tackle the security and then privacy issues. Then what about the interoperability issues? So because of we have wide variety of the devices and heterogeneous systems, heterogeneous architectures in place, how we could be able to there is a tackle this. So we have the solutions like standardized AI protocols and frameworks to facilitate the integrations across the different platforms. Had to come up with a different API systems, application programming interface that able to manage these federated environments. So AI-based orchestration systems, the more orchestration systems that manage the diversified vendors and diversified networks and diversified frameworks sit in the different systems actually. The next challenge will be data management and analytics. So with the vast amount of there is a data generated, right? Definitely we have to do the data compression techniques with the AI driven, right? Because we are going to see it's not about only the megabytes or gigabytes. It's all about there is a terabytes amounts of data to be that is downloaded with them, right? So AI driven data compressions, real time analytics, and edge AI for localized there is a data processing would be used. And energy efficiency. This is a very major concern, right? So when it comes to we are using the devices which are connected to the internet, right? So the batteries will drain, the devices will need more energy systems. Even the biggest problem with the AI, there is a data center, right? How much energy it consumes, right? So even it can bring the data center, but it consumes more energy and then more water. How you tackle this kind of issues? Definitely you have to employ with more green computing, but it's something like a not a simple AI, right, or generative AI. So any technologies we have to come up with a green AI, which means right more reduced the carbon emissions and more reduced the energy usage, right? So how we got to come up with energy efficient algorithm then right? That will have the low power hardware devices. Any neuromorphic there is a chips or any there is a PCB board designs right that come up with right more energy reduced more low power low energy devices has to be come up with for there is a green AI based there is a system there. So we have there is more problems and we have more opportunities and we have more solutions for this. Right? We have latency and bandwidth, right? So what is the difference between 5G and then 6G? So when it comes to jitter, latency, energy, traffic, localizations, user experience, right? So we have more reliable the systems with the less latency then, right? So but also high jitter. But whereas, right, so optimized more solutions will have more optimized, will have more challenges as well. We have to there is a tackling that. So edge computing in AI for 5G. So that's why we had to go with federated learning and AI model compression. There is a techniques. So not only for edge computing, there is a fog computing as well. So there are different, there is a case studies, right? So AI-driven network optimization using 5G. So the key technologies will be AI algorithms, predict the network congestions and preemptively reassign the resources. So it won't wait for the network congestions, it will automatically reassign the resources. And there are deep planning models that optimize the handovers between the cell towers that will reduce there is a drop off of calls and then drop off of any, there is internet, there is a congestion there. Okay. So there is no drop, there is a connections anymore. And seamless support for real-time applications in video conferencing in a real-time mode with the help of this IoT, there is sensors there. So we have a predictive maintenance and real-time data analytics on a network performance, and operators can make immediate judgments to optimize the performance, ensuring the stable connectivity and an improved user experience. So we will have a very reduced there is network bottlenecks, and also without any human interventions, we will have automated detections as well as the resolutions of the network issues. And the 3D rendering holographic, there is a communications model will also be provided, and the transmissions and holographic, right? So that is what we have seen in the video as well. Holographic real-time 3D experience videos. On AI optimize a V2B communications, vehicle to vehicle network communications, vehicle to network and vehicle to infrastructures. So you have more autonomous vehicles, and these vehicles will know the real-time traffic congestions and what is the movement between the traffic network, and they will take decisions very immediately, very promptly in a real-time manner. And they will also uh, give this network data to the followed there is a network customer. So this will also going to happen there is a future in a vehicle to vehicle communication networks. That's going to be very, there is a promising, because vehicle to vehicle network communications, right, that will have more there is a gateways, more there is a filters, more right vehicle to infrastructure networks should be brought on up. And also, right, the collision predictions and preventions, right? So say there is a real time, there is a vehicle sensor, right? So always it's going to be the collision detections and the prevention that should happen in a very real time manner. For example, right, ML algorithms analyze the historical data to identify high risk scenarios and suggest the corrective actions. For example, the speed reductions and the lane changes as well. So all this happens in a real time without any manual interventions. So it will automatically, right, relay by making the relative distance of its right, the front vehicle as well as its back vehicle, right, and it will right make a decision accordingly. And AI-driven safety systems reduce the likelihood of accidents. So that will, right, that will make a major impact, right, in the logistics as well as in the road. There is accidents actually. So it will reduce accidents because, so that will make accidents because the live CCTV footages, and it will make connections with all vehicle networks, and right, it will change its there is a frequency and it changes, there is a speed as well. Again, for which right we require a proper civil road infrastructure should be in place to enjoy this. So these are some of the, there is a case studies, right, for using the AI in the communications network as well as in the vehicle network. So I will pause here, right? So if you have any doubts, right, you can stop here or we'll go to the, there is a next topic then. So these are the some of the projects, 32 6G research projects to be followed. I'll also share this link to you. So there are different projects, 5G startup, satellite and terrestrial access for distributed ubiquitous smart telecommunications, self-managed, sustainable, high-capacity optical networks. Because how we utilize the 6G networks for our with the help of the AAs. So and also the green, so green technologies It's not about red simple A, so we have to use a green A for the implementation of the 6G networks. So any queries or any doubts so far? So predict 6G. So programmable A enabled deterministic networking for 6G. Towards an A native user-centric AR interface for 6G networks. There are different there is a projects that works with how we can empower the 6G communications by utilizing the A, which means the green A. Of course, the A itself, there is a evolving, right? If you talk about the A, right, it's not about simple A, right? We have to use a lot of synthetic with the help of generative A, right? And responsibly it should be, because when it comes to autonomous vehicles, right, there's more, there are securities, privacy involved, right? Then there should be a kind of, there is a responsibility. Then also comes with, now we have agentic A. There is no human intervention involved. So it can't with all other A based there is systems, and it will give you the holistic solutions in a minute, right? So that's how the agentic AI also works, right? So we have a lot of there is a matured, there is there is a technologies in place now. Okay, so now I move to the next slide. Okay, this slide. So this is about the AI in there is healthcare improvement. So how the AI revolutioning the communication. So similarly, right? So how it can be used in the smart healthcare. So already we have given some of the right inputs, right? In IoT, Internet of Medical Things, and also right we have the smart healthcare, robotic surgery in place, right? So a lot of ways the AI could be used in the healthcare environment. Right? So similarly, right, for assistance, clinical assistance, right? So it's also be used. So what about the healthcare environment? In healthcare, so we have a different kind of there is records. We call it an ECR, right? So electronic health records. So it's kind of there is a prescriptions for the doctors, as well as we have a lot of clinical reports. We have ECG, MRI, there is a scan reports, right? So we have a lot of images, a lot of video data, a lot of apart from this audio data. There are very large number of there is a data in place. So this LLMs, right? The large language models, right? So that could be place, and vision language models, vision transformers, right? So that is also placed in trained on clinical data that is in place. That is in various type of there is a data, right? All this data can be combined and make it as given as input for our LLM models. That will make a decisions. That will make a there is a predictions as well. So even right? If you go to the there is hospital environment, right? So we have a lot of the prescriptions, other medical reports that will be given to us. Simply scan this kind of the reports and give to this LLM model like that is ChatGPT, right? And uh, post queries on that, right? You will get to have kind of this idea. So what happened to the persons and what is the diagnosis is given to the patients, and what are the there is a treatment, right, that will be given to this kind of there is a patients. So AGI, so on-device inference on wearables and IoT sensors, enabling the real-time, low-latency clinical decisions. Because AGI is something like this kind of federated learning. Because the typical AI that runs in there is a cloud servers. But when it comes to environment like in a healthcare environment, so these data should resides within the clinical environment itself. So that's why we had to go with the kind of there is AJ, which is something like a federated learning environment, right? So we generate the data in a healthcare environment in a hospital in place, right? So in the within the hospital environment, we have to apply the HA and we have to make the reports, clinical diagnosis reports, and these reports should be submitted to the doctors, right? To immediately. That's why right the HA in place. So we know that, right? The federated learning is very similar to this AGA. So distributed model training across the hospital networks without centralizing the raw patient data. So this is about yesterday's model. So this is a silo. They are putting in a very discrete way of processing the records. It all happens in a batch processing way. You just submit and then you have to wait for the results, right? And fee for service incentives and anything. So now it's a today shifts. We have R4 compliance APIs, which means, right? So we have APIs for heterogeneous systems management, and we would be able to make a decision in a very quick manner. On real-time clinical data links. So all this data comes with different systems. We have MRI reports, we have ECG reports, we have the clinical reports, we have the real-time IoT sensor reports, we have the past data, we have the current data, right? With all these things in common place on different doctors, right? If a patient's admitted in the hospital and different doctors will diagnose the patients and will provide its own perceptions and give that different kind of reports. So all these reports will be accumulated or consolidated, right? And it will be given that there is a final decision about the what is a precisely how accurately that you have to give the patient's current uh, current the situations, and we have to decide carefully about the future. There is a process about there is a patients, right? He can able to make an operations or take the diagnosis of there is a patients will be. So uh, uh, hospital systems is more agile enrollment, right? And also we have to make a decision very quickly. So currently it's all happens only because of the experience of the data, right? So if the doctor is not the experience and is not have a handful of there is a data in place, right? So definitely he can make some kind of there is a wrong decisions as well, and has to wait for uh the people's there is a data as well. But if you say that, right, so when you have this kind of there is a doctor's data, so it's not kind of the replacement, it's a kind of this we say here. It is also mentioned the goal is not to replace the clinicians or doctors, it is to enhance the human expertise with AI empowered and the clinical decision the research systems. So they have all such data in place in a real-time manner. So the decision can be made very quickly and the patient's life will be there is a saved. So there are several use cases, right? The power of predictive diagnosis, like yearly cancer diagnosis, yearly cancer detections can happen with the line of models, with the Google's line of models. With approximately 99% lymph node metastasis accuracy it provides. Identify the malignant patterns at sub-millimeter resolutions and stages invisible to the naked eye. So these are the stages, right? Because how much earlier, right, you will detect the disease, right? That's a benefit you will have, right? So, but when it comes to there is a very early, right? It's we can't able to distinguish that there is this malignant, there is a pattern. So that's why the A in place. So it could be able to identify this malignant pattern very earlier. There is a stage. That's a advantage you will have it. So then it comes with not only for the cancer, but also for the cardiac anomaly predictions. We have truly ECG time series plaque arimesis as the QT prolongations. So all sort of there is a medical data comes in place and will have a better accuracy greater than of 90% now. And diabetic retinopathy, there is a screening. So the pivotal use case for point of care screening and primary care and low resource there is a settings. With a simple fundus, there is a photograph that you can take it from your mobile phones. Even you could be able to identify the diabetic retinopathy of the there is a patients. And sepsis yearly one. This is very important, right? The patients when they go for there is a sepsis stage. So we could be able to identify because the normal patients if they put in ICU, we have to put in a continuous there is a monitoring then, right? But when they go for there is a sepsis stage, right? So we have a continuous monitoring and a continuous analysis of data. So we're able to there is a predict such kind of there is sepsis in a very early manner. So definitely that will save the patient's life. So the critical stage of a patient's. So the EPICS sepsis prediction models alerts that will save the time 6 hours before the clinical criteria are reached. And of course, more sensors with the help of IoT, Internet of Medical Things. We have a lot of wearable there is sensors that are connected to the patient's body, right? And there are a lot of biological, there is a sensor, biosensors are involved, right? So that will give the real-time alerts of the there is a patients. It's not only the real-time alert, based on the real-time alert, they could able to predict the person's health very earlier. Okay. So on-device anomaly detection triggers observations posted on the EHR as well as not even the CAT teams. We are smart on EHR integrated dashboards within the seconds because since the systems are integrated, right? So these sensor will push the data to the cloud or to the edge. So that will do the kind of there is a processing, and this processing will do the predictions, and these predictions are available in a real time, right? To the there is a doctor's as well. And there are continuous monitoring with the help of there is a sensors. So transforming the operating room. So in operating room, it's not only the humans or nurses or clinicians. We have robotics, even the board, right? In if you go right through right and sorry in a row, right? You can see the right. So there are there is a surgery happens with the help of there is a robotics, right? So it's not there is a dream anymore, right? There are more robotics involved with the help of surgery because of its precision, right? It's a precisely in a millimeter or a centimeter level, right? You could be able to identify, right, there is a parts of the humans. Haptic enabled robotic arms with 7 degrees of freedom eliminates hand drummers. Air drummer filtering algorithms operate to the servometers layer allows structuring in spaces with less than 2 millimeter there is a diameter. So that's the way, right? But have it's there is more accuracy than the human than the cell. On intraoperative tissue classification during the operations, right? We have to distinguish the tumor margins, nerves, and blood vessels because we have there is a bloods coming in, the nerves, and there are spirits, right? There is a margins. So all have to be distinguished with the help of right. There is a robotics, but you have in real time there is a semantic segmentations, vision, computer vision models that could be able to easily there is identifying. So which is our nervous system, which is our blood vessels, and which part we have to operate actually, right? Guiding the resections, how to bisect the body, right, and also how you resect the body, right? It can be easily distinguished with the help of this robotic. There is a surgeon. AI guided surgical face recognitions. So typically in a surgical phase, we have dissections, clipping, and closures are involved. So in all these phases, we could employ the robotics in there, right? So it will make the dissections, clipping, as well as the closures. So it will be make a great aid for the surgeons, right, to make the surgery in a more effectively as well as more precisely, basically, right? So the experts, right, can do the surgery, right, but whereas, right, the more precisely it will aid you, and then will do the dissections of the patients. And autonomous, there is a skill assessments. So post-operative AI scoring of surgical video. These surgical videos happens, right? They will be given as a training for the right the to the students as well, the medical students. So it's a feedback given to the trainees, accelerating the laparoscopic competency curves of up to 40% versus subjective attending the reviews. So instead of right, uh, because in a typical there is surgical enrollment, right? No, the students or the people won't be there is allowed. But if you capture such kind of there is a video, so such kind of there is a training will be given to the students. So that's why right, you will have a more effective training will be given to the medical the students. That's why the surgical innovation happens. And of course, we have a accelerated drug discovery in genomics. So typically takes a 10 years to market any kind of new drugs. And also there are so much of cost involved. There are $2 billion involved cost per drug for a good drug. Of course, the 70% of the time reductions happens if you are utilizing the AI because the AI with the help of more number of there is a data. And of course, we have to think about the quantum as well. When the quantum is evolving and the AI is also evolving, so we have more synthetic data, we have more agentic there is AI in place, and we have a more drug discovery and also very faster drug discovery will happens. So it's make a revolutions in the drug discovery and then drug implementation. There is a process then. So we could be able to identify the protein structures, we'll have more generative molecular designs, and we'll have a more polygenic risk, there is a scoring there. So since the drug discovery more sensitive and has to go with a more number of trials, right? So these trials can be make it more agile with the help of the AI models. It reduces the 70% of the time reduction. So instead of 10 years, probably we can complete all trials and we could able to satisfy the drug board, right? So to approve the particular there is a drug, maybe in there is a 3 years. So it reduces from 10 years down the line to there is a 3 year. AI powered virtual health assistant, not only kind of right IOMT devices and robotic, there is a surgery, right? It also helps the clinicians with the help of virtual health assistants. Definitely, we have to thank the NLP techniques, natural language, there is a processing. So it will identify there is a context of the patients, context of the clinicians, and you will try to there is a response in a more immediate way. So in more what do you call the local language based. And so respecting of any there is a language, the clinical, there is a person, right? Is for speaking about, right? You would be able to do the language translations, it will understand the context and it will respond to there is a patients. Because all these terms, the medical terms are more complex and is very difficult to there is a crack. So whereas when these NLP ontological mapping comes in place, this AI chatbots use symptom checkers engines that will make the APIs and ADA health. There are various AI chatbots or health chatbots already in place that could be able to identify the context of the clinicians and it could be able to assess the nurses as well as the clinicians. There are more NLP pipelines that will transcribe and structure the patient's physician conversations into the soap notes and real time, which means whatever the conversation happens, usually, right, the doctor come in a very fast way because I have to visit a lot of patients and he will give the notes to there is a nurses as well as to the all clinician, there is a person as well as to the patients. So whatever the notes he has given, that should be immediately there is a transcribed, translated, and in a proper way. It should be in particular that is a context that should be make it as there is a diagnosis report as well, right? So there are more kind of the reports will be there is a generated as part of right in a clinical diagnosis of the patients. All those reports may be make it in a more accurate manner with the help of this AI powered virtual health assistant. So there are a lot of there is a challenges as well here also. We have security and privacy architectures for which you have to go with the zero trust architectures, and also we have to go with the model explainability. Explainable AI, right? The sharp and then line, right? So because we have to go with the more responsible AI and we have to more come up with the road, more explainable AI as well. So how this AI component really works with the smart healthcare system. So that should be justified, that should be convinced to the clinical persons, to the drug advisory, there is a board as well. How we can do that? With the help of only the explainable AIs. And with the help of less audit trials and more audit model costs, we go to implement the AI in a more secure way. And of course, the responsible AI in place, there are a lot of algorithmic bias will happens, but this algorithmic bias happens in the healthcare domain. There is more sensitive and there is more danger. So how we have to avoid it. So the health equity with the help of the responsible AI frameworks, we have to implement them. But of course, the final line, right? We have say regularity pathways. There is something called a software as a medical device, right? So we have a building, right? This kind of the AI solutions, which is kind of there is a software, which is also given as a kind of medical device for the healthcare environment. So we are building this AI solutions as a kind of there is a medical device. So currently we have many medical devices. So our AI solutions will also be added, augmented as a medical device as well that can be added. So with the help of this AI frameworks. So we have to integrate responsibly and also we have to prioritize the ethics and the explainability and have to lead this AI regulations into the healthcare environment. So with that, right, I conclude there is a sessions. So now we have there is a queries that we can able to address interact now. Thank you.
Thank you so much, sir, for such an insightful and inspiring session. Your valuable knowledge and expert guidance has given us a deeper understanding of the topic. We sincerely appreciate the time and effort you have taken to share your expertise with us. Now, I would like to invite the participants to share their feedback, comments, or questions regarding today's session.
Okay, I think there are no questions. Shall I leave now? Okay, thank you.
We shall now present a token of gratitude to our esteemed resource person in appreciation of his valuable time and insightful session.
Okay.
On behalf of the Department of Electronic and Communication Engineering, I extend our heartfelt gratitude to you for being with us today. We wish you continued success in all your future endeavors. Thank you, sir.
Thank you. So I'm leaving now. Thank you.
Hello. Can you hear me?
Okay, sir. Start ചെയ്തോളാം.
So we shall now move on to our next session. It gives me immense pleasure to introduce our next esteemed resource person, Dr. Jayadevan R., an assistant professor in the Department of Electronics and Communication Engineering at Government Engineering College, Wayanad, with over 14 years of teaching experience. He holds a BTech in Electronics and Communication Engineering and Signal Processing and a PhD in Image Processing. His areas of expertise include signal processing, image processing, machine learning, deep learning, and communication engineering. He has published more than 15 research papers in reputed international journals and conferences and is the author of the books Digital Electronics and Lab Primer through MATLAB. Dr. Jayadevan is also a member of the Board of Studies of both Calicut University and Kannur University. He has served as a resource person for numerous faculty development programs, workshops, and training sections, and has guided many BTech and MTech projects in emerging areas of electronics and communication engineering. We are delighted to have such an accomplished academician and researcher with us today. I'm confident that his session will be highly informative and inspiring for all of us. With great pleasure, I now invite Dr. Jayadevan R to deliver today's session. Sir, please.
Okay. Thank you, Chaitanya, for a nice introduction. I think my screen is visible to you.
Yes, sir. It's visible.
Okay, fine. So first of all, I would like to excuse me. Okay, sorry. So first of all, I would like to share my sincere thanks to EC Department of CIMAT for inviting me as a resource person for this FDP. And also, I'm very glad to get an opportunity to share my experience and some knowledge regarding the AI applications in biomedical and healthcare systems with various faculties from different institutions. Okay, now let us move on to the session. As you all know, I would be dealing with the topic AI applications in biomedical and healthcare systems. I think you had some similar or maybe some different sessions regarding the AI in the previous days and some with related with IoT. Maybe some of the topics that we deal with or deal today may be already familiar to you, or you might have already heard in some of the previous sessions. And these are the contents. So before getting into the healthcare or the AI applications of biomedical, first we will see is a story of AI, how AI has evolved out. And the latest trend or the model in healthcare called the foundation models, especially in clinical AI. Then we see what is called a multimodal AI and the basic concepts of federated learning and explainable AI in medical diagnosis. Nowadays, almost all of the research works using AI in medical diagnosis has been using explainable AI. We'll see the reason why. And one of the case study that involving this explainable AI, and the time permits some data strategies at the end. Okay. You know, every field has a story of some faults starting. And, especially this AI, just like, before we landed on the moon, there were rockets that exploded on the launch pad. Some failure stories. And, before the penicillin was invented, doctors prescribed mercury for infections. And, before the transistor, there were unreliable vacuum tubes having the size of our fist. So AI stories, it's also not different. We will actually explore through some eras of AI. Actually, there are three eras of artificial intelligence are there. And you know, the reason of three eras means we have not succeeded in the first era. We have not succeeded fully in the second era. We need the third era. And we cannot ensure that we are uh, we have succeeded in the third era also. We may be moving towards a fourth era, and we will see fifth era. No one can predict that. So depending upon the evolution of the other things, like the computing power, the data, the algorithm, and all, the AI has been progressing. Actually, when you take the age of AI, there is actually, we need to tell a 75-year-old story were the first era that began in the year 1950. And we call that era as the era of symbolic AI. That is the first era, and that continued up to late 1980s. So, you know, a professor at MIT named Herbert Simon, who later won the Nobel Prize in economics, he made a bold prediction that machines will be capable within 20 years of doing any work that a man can do. He predicted the same in 1965. You know, he was one of the sharpest minds of the 20th century. His prediction was based on a reasonable assumption that intelligence is nothing but computation. So if you can write down the rules of how an expert thinks, if you can capture the logic that a doctor uses to diagnose a patient, or a chess master uses to evaluate a position, then why not a computer, which is good at following rules, should be able to replicate that intelligence? So that was his prediction. And that was this foundational idea of symbolic AI called rule-based AI or expert system. An interesting example is cited over here. In 1972, a team at Stanford University built a system called MySyn. And that was a AI system. Its job was to diagnose bacterial blood infections and recommend antibiotics medicine for that. So diagnose the bacteria in blood and recommend antibiotics. And they interviewed expert physicians, the best infectious disease specialists in the country, and they spent several months for translating their clinical reasoning into some rules, like if-then rules. Rules like if the organism is gram negative, the organism they have identified is gram negative. Gram negative in the sense that if you conduct a pathology study in laboratory, if that particular bacteria or organism did not produce any particular stain, like pink stain or violet stain, something like that, then we call it as negative, gram negative. And the site is blood, if it is found in the blood. And one more condition, and if the patient is compromised. Okay, compromised means it's a weak patient. So if these three rules satisfied, then there is a strong evidence with a high probability that the organism is pseudomonas. So if these three conditions are positive, the pseudomonas organism is present in the blood. So that system developed by the Stanford University experts was just like a rule engine. They hand-coded several rules in medicine. Nearly 600 plus such rules were developed. And they built that system. So no doubt that MySyn worked remarkably well. And in several situations, it outperformed several junior physicians and performed at the level of specialists. And the medical community was astonished at that time, and newspapers at that time called it a doctor of future. But later, there was a problem. These 600 rules built by a team of knowledge engineers, it was only for one type of infection, the infection caused by Pseudomonas. If you wanted the MySyn to diagnose another disease, say pneumonia, you had to start again from the scratch. If a new antibiotic was discovered, you have to manually update that rules. So if medical knowledge changed, the system became outdated just overnight. And the system was actually not learning anything. It was just executing some knowledge. Okay, so that is why we called the first era as the era of just the rules. Just implement those set of rules. Okay. And another brittleness of this era happened in 1980s when a company tried to build an expert system to handle the customer service calls for a telephonic company. So similarly, with the help of several experts, they formulated several algorithms. When a customer called, depending upon the question, several rules are encoded to answer that. At the first day itself, that system crashed because the customer asked a question that to compare two plans, say one standard plan and a premium plan. The system crashed because there was no such encoded rule to compare two plans, just to provide information regarding the plans or just to provide the direct information. So the experts of AI at that time, they realized that this type of AI algorithm development did not work. And later, that period, and twice in 1970s and in the late 80s, the funding actually dried up at that time, and the works started to get paused. And we will call that period as AI winter. Okay, that was the first wall of this AI era at that time, or the first failure we call. Okay, next we see the era 2, the era of classical machine learning. It began during 1990s and continued up 2011. We call this era as statistical machine learning. You know, from the previous era, we could realize that we cannot write down all of the human knowledge and then implement it. So what we should do is we should allow the machine to learn from the data. That is why we will call as statistical machine learning. And it was actually a revolutionary concept. You know, the key insight was instead of a human expert writing rules, we will collect large number of labeled examples, and you let an algorithm and the mathematical patterns that distinguish two or more categories. And you know, some of the successful algorithms of those that era was support vector machines, decision trees, random forest, KNN algorithms, then gradient boosting, etc. In the year or early 2000, you know, spam email was an crisis for internet at that time. And by 2004, almost 80% of the email traffic was contaminated with advertisements, spam advertisements, scams, malicious links, etc. So mostly email was felt to be becoming unusable. So at that time, a computer scientist called Paul Graham, he published a paper in 2002, and he proposed a solution using Bayesian probability. And those who are familiar with AI or Bayesian rule might have done some problems related to how to detect whether an email is spam or not with the help of certain words. So what the idea was that he just simple, look at the words from a collection of thousands or 10,000s of emails, and that humans are labeled as spam. Then you calculate the probability that each word appears in the spam email and what is called in legitimate email. And for any new email, you multiply these probabilities, conditional probability, posterior probability, those terms you are familiar. So using all these probabilities, you will be able to classify whether an email is spam or not, if a particular word is present in that. And this approach became the backbone of Gmail, Yahoo Mail, and Outlook spam filters at that time. It was actually, it was not at all an intelligence in any deep sense. It was just a pattern matching. We are checking some sort of patterns in that and just find it out. You know, this pattern matching will work in small scale or in narrow problems. Another interesting story called Netflix price story, and that happened in the year 2006. In 2006, the Netflix was primarily a DVD company, DVD by mail company. They offered a price, $1 million prize, to anyone who could improve their movie recommendation to the users by 10%. Anyone who proposes an algorithm to improve their recommendation accuracy by 10%, they will be awarded $1 million prize. So several teams from universities and companies completed this, and they worked on it. They applied some different techniques from machine learning, classical machine learnings like the mathematical ideas. And after 3 years of this competition, a team finally crossed that 10% threshold, and they claimed the prize in July 2009. Okay, one team won that event, that challenge, and they got the prize. But unfortunately, Netflix never used that algorithm. What is the reason is simple. They won the challenge by the year 2019. Actually, the challenge started in year 2006. So by 2009, the company had shifted entirely to streaming from the concept of DVD. So what happened because of that? The viewing patterns of the streaming users were completely different from the DVD renters. So the algorithm that was proposed, it was actually for the DVD renters, not for the streaming users. So the model that had trained on one data is not fit for a data that is coming in the future. I mean, the distribution of the data had shifted, and very sad, the $1 million algorithm, it was obsolete before it was deployed. And this story captures the central limitation of the classical ML era, because systems that we built they are powerful, but they are brittle. They are not adapted to the change. So the deepest problem in this era too was feature engineering, which means for an image classification system, if you want to classify a set of images, the human engineer had to develop an algorithm. Moreover, he has to decide which type of features we will extract from the images, whether I will use edge detection, whether I will use histogram features, or whether I will use text descriptors, etc. So that is machine learned from those features. Those features are actually derived by human beings. So that was the issue. That was the wall of era 2, actually. Then came the next era, that was in the year 2012. The era started from that year. What happened at that time? On September 30, 2012, a PhD student named Alex, you might have heard that, AlexNet. So he submitted an entry to ImageNet challenge. That was one of the most competitive computer vision challenge at that time. And prior to that year, I mean, this happened in 2012. In early years like 2011, 2010, etc., the dominant approach to image classification or image recognition was just to manually design some mathematical features. As I told earlier, we can derive edge detection, we can derive texture, we can derive gradient histograms, and feed these features to machine learning algorithms. That system will do the classification. So the accuracy that the earlier systems achieved was just around 73.8% for that data set. Then in 2012, Alex proposed a new network called AlexNet, which could achieve an accuracy of 84.7%. So compared to the previous year, that shift, that gap is 11%. But during the previous years, when you take the difference of 2010 to 2011, the difference was just like 0.5 percentage or 1 percentage. But suddenly from 2011 to 2012, what happened? The AlexNet introduced a new architecture which could achieve an accuracy greater than by 11 percentage. So that was a drastic shift. Some of them, even some experts, they believed that it was an error, but actually it was not an error. It was the real beginning of a new era called deep learning era. So what was actually happened there? He proposed a system called AlexNet, whose backbone was convolutional neural network. So that was the birth of CNN at that time. So in this system, what happened was the network will be allowed to learn the features. I mean, the system will algorithm or the system itself learn features from the input. If you are giving an image, that network will learn features directly from pixel data rather than features designed by human beings. So in that system, the earlier layers will learn features like, the basic features like edges and gradients. In the middle layers, it learned more advanced features like textures, shapes, and in deeper layers, it will learn higher level concepts. And this is not a programmed algorithm. It is emerging out from that. This learning process is getting evolved out from that network. And this is one of the representation of how this deep CNN is getting learned. Actually, CNN has got different layers. As I told, earlier layer, this is an earlier layer, which is learning only low-level features like edges, different orientations, the vertical, horizontal lines, inclined lines, etc. So whatever input or image you are giving, they are just learning these type of low-level features from the earlier layers. When these learned features when these input activations are getting passed on to the middle level layers, convolution layer 2 or some few higher layers, they started learning even more higher features like shape, textures, colors, etc. And when we move to even higher stages or higher layers, it began to learn the real meaning of that image. As you can see, when you move to the third layer, it started learning the actual meaning of that input image, whether it is a face or all our face. So how it distinguishes between different persons. That is called a semantic concept. So after that, it was actually an explosion of deep learning. So we are now in 2012. Let's see what happened in 2014. In 2014, another researcher, Ian Goodfellow, and his colleagues invented generative adversarial network. That was also a revolutionary contribution. For the first time, machines could not just classify images. They could generate entirely new images just from random noise. So these implications was actually astonishing. And in 2015, then came, that was, I think it is not shown in 2015. Actually, in 2015, another remarkable achievement called RusNet, similar to AlexNet, a more deeper network called AlexNet came, which could won this ImageNet challenge, and it could surpass the human accuracy of 94%. And that network was 152 layers deep, RusNet, and it solved the problems of vanishing gradients with a concept called residual connection. And in 2016, then came some models like AlphaGo from DeepMind. They could defeat the experts of even the champion of that game. That was also a revolutionary contribution. Then came in 2017 another network or another contribution that was a real stunning contribution called transformer. We'll see that next. And before looking into the concept of transformer, we will see this sentence first. So this explains how the transformer works. You can see that this is just an English sentence. The animal did not cross the street because it was too tired. Okay, you can see that the word it has, it is given in bold. What does it refer to? It is obviously clear that it is nothing but the animal. It refers to animal. A normal human being can easily, one who understands English, you can easily understand that the word it is directly linked to animal, or it directly refers to animal. Now, when we give this sentence to a model, a sequential model, which will predict or which captures the information in sequential data, you can take the example as LSTM network. LSTM network is a sequential model that we use in this type of applications. It was prominent until 2017. So how this LSTM learns sequential data like this is that when it reaches it sequentially learns. First it look into the word the, then it look into the word animal, then it look into did. So by sequentially, LSTM is sequentially processing each word in a sentence. So by the time it reaches the word it, this has already processed many words like crows, not, did, animal, the. Okay, so how it is getting processed? The information about the animal, that is 4 words behind it: crows, not, did, and animal. So animal is 4 words back to the word it. Actually, this LSTM is encoding the information of each word in a fixed size memory vector, and that information is getting overwritten if you pass each word. So when it reaches the word it, the information regarding the animal has more or less overwritten. And we call this as a long range dependency problem, which means that if the 2 pieces of words or the 2 words are apart in a sequence, the harder it is for an LSTM to connect, or it starts forgetting. This issue is resolved in the model called transformer. Now let us see what the transformer is doing. The transformer, unlike LSTM, it is not reading the sentence sequentially. Instead, every single word in the sentence simultaneously looks at every other word. For example, if you take the word it, this it will scan or it compares this word with all other words in that sentence simultaneously. We call that mechanism as self-attention. Okay, so you can see that here a golden color arrow has been projected from the word it to the animal, and over that it is written in here in golden letters, high attention 0.92, which means this word it provides high attention to the word animal, and that attention is scored 0.92 or 92%. It means that between each pair of word in a sentence, an attention score is computed. That's the concept of transformer. If you take a sentence, a long sentence or a big paragraph, each word in that text will compare with every other word, and for each such pair of words, an attention score has been computed using this equation. The equation here, attention equal to softmax q k t divided by root tk into v, where q is queries, k is keys, v is values. So q means what is the input we are trying, and k stands for the keys related to all other words, and v stands for the values. Okay, so after computing this, you can say that you have a list of attention scores for every pair of words, and from that you can determine which word is more connected to the other word. And you know the k and the v they are already developed from a set of pre-training, not the values provided by the user. So what is the advantage of using a transformer model like this? This is not limited to a language model. You can use this beyond a language, which means that any sequence, the concept is any sequence can be tokenized because each word can be tokenized. If you take a image, the pixel can be tokenized. If you take a music, the notes can be tokenized. And if you take a ECG, epochs can be tokenized. If you take amino acids in a protein, those are also tokens. So whatever data you have, that data can be tokenized. And we are comparing not just the words, we are comparing the tokens. So whether it is a language, whether it is a image data, video data, whatever it is, you can tokenize every data. And those tokens are given as inputs to this transformer. Okay. And this concept is also used in to develop AI models for playing chess, because the movements in the chess can also be tokenized. Okay, and that was era 3A. So after the invention of the transformers, era 3B began. That was the era of foundation models. It started from 2020. In 2021, actually, a group of researchers at Stanford published a paper, and they coined a new term called foundation model. What was that? The definition they have given is quite simple. This is a large neural network and almost always transformer. This is nothing but a transformer, but it is trained on massive and diverse data sets and designed to solve one specific problem, but to serve as a general purpose foundation for a wide range of downstream tasks. Which means that it is just like building a large, if you go for constructing a large building, definitely you need a foundation. On that foundation, you can build anything. You can build a shopping mall, you can build a hospital, you can build a school, etc. So here what we are doing here is you are training a transformer-based model on a massive and diverse data set. That forms a general purpose foundation model. Then you can later develop, or you can later train this to any specific application. You can see a good example here. GPT, the third version of the GPT-3, that was in 2020. OpenAI released GPT-3. And, that was actually trained for 570 gigabytes of text. And the model was much complex. It had got around 175 billion parameters. So one researcher tested this GPT by giving 3 examples of a language translation. He gave 3 examples of English to French translation. Then after that 3 examples, he gave a new English sentence. So without further training, GPT-3 translated it fluently. Another researcher used the same GPT-3. He gave just 3 examples of code generation. Then after that 3 examples, he just provides some prompt in English. GPT simply wrote the code. So actually that GPT-3 had not been trained on English to French translation or code generation explicitly. These models derived these capabilities, and those are emerged from training on enough data that the model had already internalized. The structure of the language, the logic of the program, and even the programming syntax, everything this model has already learned by the training of this 560 gigabytes of text. If you want to use this for a particular application, you just need to that model just need to do a context learning. We call it as a few short learning or context learning. There is no need of updating the weights. So this was the moment the AI community realized that the scaling is not just making models bigger, it produces qualitatively new capabilities. Okay. This shows a foundation model paradigm. That is, you have one model and it serves many applications. That means a single large model pre-trained on diverse data sets serves as the base for diverse applications through fine-tuning. You have enormous applications here. You can generate code, you can analyze legal data, you can perform language translation, then you can go for drug discovery research, you can use it for customer service, image generation, scientific literature, medical diagnostics. Okay, so that is the way the foundation models are developed. Now we will see how we will use the foundation models in healthcare. Okay, we can see a text that is printed over here. 65-year-old male, comma, history of atrial fibrillation, comma, currently on warfarin, presenting with sudden chest pain and shortness of breath. Chest X-ray attached. What should be the next step? This is a sentence structured with medical terms. So suppose that this is a sentence drafted by a medical expert and provided to a generic language model, say ChatGPT or something, earlier versions of generic language model. What will be the response from that model? Obviously, they had to face many issues because the foundation models, we'll see the foundation models for clinical AI. The reason is that generic LLMs always fail in clinical settings. We'll see the reason. First of all, at that time, there was no facility to input the images. So it cannot see the X-ray. In the sentence, it was mentioned that chest X-ray attached. So we have no option to attach and it cannot see that. So a plain text LLM has no eyes. There is no, it will not taken into account the chest X-ray attached. That is one problem. Second problem is hallucination. Hallucination means the model has no internal sense of what it is speaking or what it is generating, which means that it cannot distinguish, like, I am guessing whether it could be like this, or whether I actually know this, or whether I am confident in with my response. Okay, it is built only to produce the next most statistically sentence or word. That is the only work that LLM is doing. For each current word, it will produce the next statistically possible sentence or word. So it produces answers with full confidence. There is no scope of doubt in the output of LLMs. So it produces answers with full confidence, and the readers have no option whether LLM is in doubt or with half confidence or fully confidence, just like a normal human being speaks. So that is actually a very dangerous situation. Third one is language mismatch. Means generic models are trained mostly on everyday internet writing. It may simply not parse the clinical shorthands correctly. It may not be able to get familiar with the medical terms because it has seen very little text written like this during the process of training. Another issue was actually these models, the LLM models, especially generic LLM models, they tested on exam questions of different subjects, engineering subjects, medical subjects, other art subjects, or different subjects. These models are tested. And in those exams or exam questions, you have a clear scenario, you have 4 answers, you have 1 correct answer. So At that time, the issue is there is no issue. But here, at this point, the patient is not like an exam question. The patient is just has a lot of messier. I mean, the chest pain could be cardiac. It can be pulmonary problems. It can be some acidic problems, etc. A real patient arrives looking rarely arrives like with a clean question or like normal that you face in an exam. And at that time there are if you go for a real situations, you can see similar ambiguous cases this LLM has to face. And another issue is, if the model is wrong, there is no way to ask it, why did you say that, and get a trustworthy answer. You can ask it to explain itself and it will generate an explanation. But that explanation is itself another generated guess, not a genuine readout. And one most important thing is that this model does not know nothing real about this specific patient. This particular patient has got so many issues, like current medications will be there. He has got some allergic histories there, and similar issues will be there. He may be taking or skipping some type of medicines. So patient-specific information it is not at all available. It is only providing general outputs. So with all these issues, a generic LLM is not fit enough to deploy as an AI support for clinical diagnosis. The generic LLMs unfit for clinical settings. They were GPT 3.5 that launched at November 2022, even GPT 4, then Palm and Palm 2 models developed by Google, then model developed by Meta, Llama model, Blue model, etc. These are all cited from this paper called Capabilities of GPT-4 on Medical Challenge Problems. Because in this paper, an analysis was conducted on 2 sets of official practice materials for USMLE, that is a 3-step examination program used to assess the clinical competency in the United States. So they also evaluated their performance on multimedia question answers, etc. So GPT-4, without any specialized prompt crafting, exceeds the passing mark of that test by over 20%. So if the 50% is the passing mark, GPT-4 scored 70%. So that was a performance of GPT-4, but still we are saying that this is unfit for clinical setting. So the reason that we had seen because of 5 or 6 drawbacks are there. So what we should do is we know that these LLMs are built on some foundation models, but that foundation itself is not at all required to decide whether this foundation is built for a hospital, whether it is built for a shopping mall, or whether it is built for a school or a college. We have to fine-tune it. So in that situation, or this has led the research community to use the general purpose foundation models for medical specific tasks. What they did was they pre-trained the data on enormous and unlabeled corpora, which means a large collection of text. They started training this on a large collection of text, not just text, medical documents. And they later adapted to this to many downstream tasks with very little training. In healthcare, such approaches really matters because in biomedical applications or in healthcare, we don't get enough labeled data. Whether it is a clinical data or image data, labeled data will be very scarce, expensive, and bounded by certain laws. But unlabeled data, that will be surplus. There are a lot of data sets like PubMed abstract, clinical notes, medical textbooks, etc. They are comparatively much abundant. So we can use the concept of using unlabeled data for training. That is also possible. So, how this unlabeled data is used for training these LLMs. you might have heard that if you have a sentence, you can generate so many sentences from that single sentence. How it is possible? Once you have a sentence, you can skip many words or you can mask many words in that sentence. Different combination you can mask. And the model is allowed to predict those masked words given you have a collection of unmasked words. Okay, the real data is there. From that real data, you will randomize it to generate a large collection of other data. Okay, that is a concept of training this LLMs for biomedical data with the help of unlabeled inputs. And we will see, there are 3 case studies or 3 models we are going to discuss how these foundation models are used for healthcare. First one is MedPalm-2. How this MedPalm-2 is developed. Actually, this is not a MedPalm-2 is not a model trained from scratch on medical data. It is actually built from Palm-2 model. We have seen here Palm-2 model developed by Google in April 2022 and Palm-2 in 2023. So they took the Palm-2 model and they adapt it to 2 stages. Here you can see what does the Palm-2, how does it perform? This Palm-2 model is adapted in 2 different stages. Initially, you have general purpose Palm-2 model. The stage 1 is that it is instruction fine-tuning. Instruction fine-tuning means you have a question answer pair. I mean, initially you will have some set of biomedical data, MedQA, MedMCQA. So many biomedical data are there. Altogether, we will say it as multimedia QA. So we will form question answer pairs from this set of questions. And this will be the input to Palm. Stage 2 is novel inference time strategy called ensemble refinement. Ensemble refinement. That is what is shown in this figure. So once you have the input, I mean the question answer pair, you will feed a question to this Palm-2. That Palm-2 will give you an answer. The questions like if you provide a simple question, like you will say some symptoms of a patient and you will ask Palm-2 to diagnose that particular patient based on these symptoms. You will ask first. So it keep on reasoning. The Palm-2 keep on reasoning and it will provide one answer. So if X is your input in this equation, X is your question, at the first time when you ask it, it will produce your answer or reason as R1. You keep on asking the same question, it will produce the answer R2. So suppose you repeat the same question to that model Palm-2 K times, you will get K different answers. Then what we are doing here is we will show, finally we will show all these answers. You have K answers. We will show all the K answers again to the same model. And we will tell it to combine this and to produce one final answer. So it will do the reasoning again based on the reasoning of different answers. And we will call this as ensemble refinement technique. This is just like we are asking or we are putting a set of symptoms to 5 different doctors and collecting the opinions from these 5 different doctors. And finally, we will end up in a conclusion. Okay. And, this was one of the best models developed at that time. This could score 86.5% accuracy on MedQA. And that was a big increase at that time. And 75% accuracy on PubMedQA. So that was a concept of MedPalm-2. Next come BioBert. Actually, this BERT, B-E-R-T, is the full form is bidirectional encoder representation from transformer. Bidirectional encoder representation from transformer. That was actually a groundbreaking deep learning model introduced by Google in 2018, developed for natural language processing. So this model allows the machines to understand the context of a word based on all of its surroundings. If you have a sentence, this model could understand the context of a particular word both from the left and right part of that word. That is why it is called bidirectional. So this uses a transformer-based encoder-only architecture. It uses only encoders, which analyze the whole sentence at once. And two major processes are involved in this. In this BERT model, two main processes are involved. One is MLM. You can see here MLM. MLM means masked language model. What you are doing here is, if you have a sentence, you will mask random words, and the model learns to predict them using the surrounding text. So using that strategy, masked language modeling strategy, you are using an objective function here. Here M capital is a subset of masked words, and X bar M indicates the current data available, I mean the unmasked data. So this is a conditional probability function, P of Xi given Xm. So given unmasked data, you predict the masked data and taking the logarithm, negative logarithm, subject to certain conditions, constraints. So this is the objective function of this. The next one is LNSB. That is a second stage, next or second capability. Next sentence prediction. If we have a sentence, if you are given two sentences, sentence A and sentence B, you will have to predict the sentence, whether sentence B follows sentence A, and for that you have Y and Y gap. Y is the label. Label means if sentence B follows sentence A, Y is true, which means 1. If B does not follow sentence A, Y will be 0. And Y cap is the probability that the sentence B follows sentence A. So this is actually a expectation, expectation equation, and we are using this as the objective function. So adding these two, you will get the total objective function of the BioBERT. So this BioBERT is after these two training steps, like MLM training and NSP training. Right? The data is initialized from BERT. Sorry, not data. Weights are initialized from BERT. That is, the BERT is the basic model on which we are building this bio. And for training, you are using the data from PubMed and PMC. That's a biomedical data set. And you are doing the training subject to these two objective functions. And based on this, you can fine-tune this trained BioBERT later to perform tasks like named entity recognition. You can see here named entity recognition, which means if you are given a set of clinical text, you can find or you can classify what each word belongs to. Just like the sentence, the aspirin is prescribed to cardiovascular disease. So the word aspirin is recognized as a medicine. Cardiovascular is recognized as a disease, similar. Okay, but this model, this model cannot generate a full sentence, because this is just to analyze a full sentence, analyze or capture the context of each word in a sentence. So when you provide input for training, we are not providing the full sentence. You are just finding or learning the context of each word. So to generate biomedical text, we are using another model called BioGPT, which is a decoder-only transformer. In the previous model, that is, BioBert was an encoder-only architecture. This is a decoder-only architecture. It was built on GPT-2 as the backbone with 24 transformer decoder layers, and hidden size is 1024, and it has 16 attention hertz and a total of 347 million parameters. And it is trained on 15 million PubMed. So the idea of this model is that this is objective was to just like casual language modeling, just like in this equation, this is again a conditional probability. If you are given x less than t, t indicates time or the position. If you have a first three words of a sentence, you will be able to predict fourth word because t is equal to 4. So x less than t means if your initial three words are there, what is the probability that at the fourth position that word will be x? So that is objective function we are using here. This is a generative model that you are using for biomedical text. Then another model is clinical BERT. It addresses a different problem from BioGPT. This needs to understand unstructured clinical text, not a structured sentence. Previous cases we mentioned was a structured clinical text. This is unstructured clinical text. It can be discharge summaries, nursing notes, etc., which have different statistical properties from the normal data sets like PubMed abstracts, etc. They may be shorthand abbreviations, ungrammatical phrasings will be there. Okay, so the data set used was Mimic3. Mimic3 notes was used for training. Mimic means it is a medical information marked for intensive care. That is a full form of Mimic. So it is actually a large publicly available clinical data set developed by MIT laboratory. That is around 40,000 patients. Those includes discharge summaries, nursing notes, physician notes, radiology reports, ECG reports, etc. So after training this BioBert, this is actually built on BioBert. So after training this BioBert on this Mimic data set, it could learn these sorts of clinical jargons and what is called the document structure of unstructured clinical documents. And later you can this particular model is later used to predict the readmission of a patient after 30 days. Sorry. X is the input that you are providing that is learned from this clinical text. X is the input clinical text that can be the discharge summary, physician note, etc. So it predicts that whether that patient will be readmitted within 30 days. For that, it is using an equation like this. CLS of X means the feature vector corresponding to that clinical note. From that clinical note, a feature vector is derived, that is CLS of S. Then W is a learnable weight matrix. B is bias term, and sigma is activation function. So it will provide a probability. Based on that probability, it will predict whether that patient will get readmitted within 30 days. So these are the different models we have seen for a clinical AI, models based on foundation models. Okay, next we will see the importance of multimodal AI in biomedical. Now so far we have seen only biomedical inputs. Not biomedical, sorry, clinical inputs. A doctor, how he diagnose a patient means he's not just relying on any one input, whether it is the clinical history of that patient or whether it is only based on, may not be only based on lab records. He may be using multiple types of data. It can be clinical history, lab reports, then imaging data, X-ray, CT, etc. So we will have scope for so many different types of data. We will have to combine this. As far as a doctor is considered, he is referring multiple documents, multimodal documents parallelly. So how we enable a model to learn multiple documents like textual inputs, genomic inputs, lab inputs, etc. Okay. So single modality, actually it has a ceiling, because as I told you, these real clinicians always make decisions on different types of data. But whether when a model combines all these features, how actually we are combining this? There are so many issues we will have to deal with. So, for example, these data are heterogeneous. Images means you have a set of pixels. Then electronic hospital records are there. Those are simply text. And ECGs, they are one-dimensional data. EEGs are one-dimensional data. So combining different dimensional data, different type of data, formats, all these are issues. So we will see how to compare, how to combine these inputs based on simple concepts. Actually, we'll discuss 3 fusion strategies. Here you can see this is actually, this image has been taken from a paper that is listed here. Navigating the landscape of multimodal AI in medicine. You know, the first one is an example for a technique called early fusion. Actually, we'll discuss this slide after. I'll discuss this slide after discussing the strategies. We'll discuss a first strategy called early fusion. What we are doing here is we will simply concatenate the features derived from different modalities. For example, the first one, F image, is the feature derived from the image. Text is simply from clinical notes or some reports, and another from genomics. So 3 different modality inputs are there. So these features are simply combining to form a new vector, and based on that new vector set, it makes a prediction y cap. But you know, this type of concatenation has several issues because you know different scales are there, different types of informations are there, different dimensions are there. So practically, or in nowadays, we are not going for a fusion strategy similar to early fusion. Another one is late fusion. Late fusion is that we will build different models for each inputs. For YCAP image is it is actually a prediction made by a model that uses image input. YCAP text is a model developed to predict based on textual inputs, and YCAP G is based on genomic input. And we will provide different weights for each prediction. Alpha 1 is the weight for the prediction based on image. Alpha 2 for textual, alpha 3 for genomics, such that alpha I, that is normalized, sum of all alpha is equal to 1. So depending upon the significance of each model, you can, that is also a optimization strategy. You will have to find the significance of each model and you will form the different values for alpha. And you can easily validate this also, because you can audit one decision at a time and you can analyze the importance of it. So that is called late fusion strategy. Another is joint or intermediate fusion strategy. In this, one example is if you have an image and if you have a text. So we will compute the attention score between the image and the text using the concept of computing the attention of Houston transformer. And we will call it as a cross attention. We are finding the attention score between the, just say, a chest X-ray input. And if we have a lab report, one is an image and other is text. So as you know, this transformer it deals the data in the form of tokens. So if you will convert image into a set of token, will convert your lab report text into another set of token. Then you will find the attention score between these set of tokens, and we'll get a probability value that will be the attention score. And that attention score will be used for further prediction. So that is actually a combining or the fusion that happens in the middle. Before making any prediction, you are combining these two data. And this type of models we are using in LavaMet and MetFlamingo models. Next, we will see a case study for this. Okay, before that, we skip that slide. This is, as I told you, it's taken from a paper like this. Here it shows 3 fusion strategies. In the first case, the first one is an early fusion model. These 2 different inputs are combined. One is a lab based and other one is an image based. This is an image based and this is from a laboratory slide or something like that. So we combine initially to form a final output. And the second one is intermediate fusion. The tokens derived from each input are combined and later make a prediction. And the third one is that's a late fusion. You are making a prediction for this input, you are making a prediction for this input, then you are combining these 2 predictions to form your final output. And now a case study. This is taken from another paper that is a novel multimodal fusion framework for early diagnosis and accurate classification of COVID-19 patients from X-ray and cuff audio. So they have used 2 inputs. One is test X-ray and other is cuff audio. So for the patient database you have here, you have taken n patients. And for each patient, you collected a chest X-ray. C1 is chest X-ray, D1 is audio. Similarly, you have for all patients. And you will definitely go for some pre-processing operations for image and audio. Then features are derived from chest X-ray. You derived set of features C1, C2, C3, Cn. After segmentation and all. And feature extractions you have taken from audio samples, which can be, after converting that audio, cuff audio into spectrograms. And we can take features like mel frequency, septal coefficient, or something like that. So after taking these features are then combined. And then you make the classification, okay, whether it is COVID or not a COVID. Another important approach in biomedical AI is federated learning. Consider a situation in medical field related to the data availability. So as you all know, when we take the diagnosis of a rare cancer subtype, it is very clear that if you take a single hospital, you will get only 10, 20 or 30 cases per year, or if you take 2 or 3 years. If the subtype is very rare, you will get only such case. And that 20 cases or 30 cases is not enough to train a generalizable deep model or even a foundation model, as we have seen. So what we have to do is we have to collect data from different hospitals. But it is there are several legal issues, or definitely illegal, or because of the patient privacy silos and all, that is quite illegal. So what we have to do is we have to take the help of federated learning, which means instead of the problem is that we are collecting data from 10, 15 or 20 hospitals. Collection of image data requires a lot of procedures. Like you have to form the ethical committee, you have to get consent from the patient for which purpose we are using that, and we have to de-identify that data. So many procedures are there. So that process is actually a cumbersome task. So what we are doing here is instead of moving your data to a central server, you are moving the model. I mean, inside each hospital, there will be a local computing machine or a local server. So you are moving your model to that server. Okay, each server or each site trains locally on the private data available in that hospital. So if a hospital has got only 50 images, the model will be trained on that 50 image. If another hospital has got 100 images, that model will be trained on those 100 images. Similarly, you will train that model on n different hospitals, data from n different hospitals. And instead of moving your data, you are sending that model parameters to a central server. For example, as I told you, each hospital is training the data locally. So here, this is the updation of weight rule formula. You have theta t is your weight, and theta t means the teeth epoch of the training. So at teeth epoch, you are updating your t+1 epoch, you are updating your weight using this equation. You are taking the gradient of your error function or loss function, and you are multiplying eta, that is your learning rate, and you are subtracting theta t, this value from theta t to get your new parameter. So after each epoch or after a set of epoch, you will send these parameters, updated parameters, to a central server. So you'll receive updated set of weights from n hospitals, and you will combine or finding a weighted average of these weights in the central server. And how do you determine the weights? That weight is given by small nk divided by capital N. That is proportional to the local dataset size. If small nk is the number of data in kth hospital, that nk divided by capital N, where capital N is a total dataset. So depending upon the dataset size, the weight will be more. So after updating the weight, you will again send the new model to these n hospitals. We will do the next training epoch, again update the weight, you resend these updated weights back to central server. You keep on doing this. Okay, so that is the idea behind federated learning. And this is a not a case study, that's a information taken from this paper. Federated learning enables big data for rare cancer boundary detection. It's a paper in 2022. Here, they collected the data from 6 continents, 71 sites over a total data set of 6,314 cases. The training process was initiated when this collaborator, they connected securely to their central server with the help of behind a firewall, and at the University of Pennsylvania, where they conducted this. So they trained this model to delineate different tumor subcompartments. Based on the architecture they had used was a 3D RUS unit for segmentation, and they used the parameter called dissimilarity coefficient. Equation is given over here. And they run their training process for 73 rounds, and they later got the result. And this code for this work is available from GitHub. Using this link, you can go check for it. So that is the idea of federated learning. Okay, next comes explainable AI. Explainable AI in medical diagnosis. What is the significance of explainable AI? Suppose if you visit a doctor with a health concern, the doctor examines you and he will give you some statement, diagnose you some statement. Definitely we want to know why that particular treatment was recommended, or why this medicine is recommended, or what is the reason of this disease. We need an explanation, not just a prediction, or not just a single answer, single word answer. So today artificial intelligence, it is making important decisions in all fields, whether it is healthcare, finance, education, or whatever it is. These AI systems are providing highly accurate predictions, but they are not explaining it why it made such a prediction. So definitely we should say it is a black box AI. We are not aware of what is happening inside that model. We are providing an input and just getting an output. That is why it is called a black box AI. And we need some more transparency. So without this transparency, especially in medical cases, suppose the engineers or the AI experts have developed a model to predict or diagnose a disease, and we have shown this model to the doctors or clinical experts, and we are saying that this model predicted like this. But in some situations, they won't be able to listen to us, or they need justification why this model predicted like this. So for accepting, to get an acceptance from, the clinical validation, we need to provide a explanation also. So high accuracy is not a matter. Means if you have a model with a 99 or 98% accuracy, but still it is clinically useless because it cannot tell why it happened. So that is not what we are expecting. We need to get why it happens. So we need an interpretation, especially explanation. So, even it is for a normal user or for an expert. So we will discuss three dominant techniques in explainable AI. One is GradCam, the other one is SHAP, and the third one is Live. Okay. First, we will see GradCam. Here, the image A and G, you can see here, A and G, both are same images. It is the original image we have taken. Second one is, it is actually this is not a image form, it is a map. We call it as a saliency map. Saliency map means that saliency map will highlight the prominent features or prominent pixels in that image, showing like the edges or other prominent features in that image, showing which object it is. So both the first one, it shows some prominent features of cat. Also, we can see some prominent features of dog. And the second one, we see some prominent features of dog. But these two images, it is not at all good enough to predict. In the first saliency map, that is in the image B, it tried to say that this contains a dog, but this contains cat, but still it displays the features of dog also. So what we need is, if we want to say this image contains cat, it should focus only on cat. That is what is shown in image C and D. In C, this is actually a heat map image, because we are highlighting the prominent regions of cat using different colors. But this is GradCam cat means these are the particular region, prominent regions of cat. And in this case, this is the prominent region which shows that this image contains dog. Okay, so this is the actually just to show how GradCam works. And the image D and J is the guided GradCam cat. By combining this saliency map and the heat map, it produced. So in the image D, it is shown, it is highlighting only the region of cat with the color and as well as the prominent pixels. And in this is for dog. And image E and K is another type of representation for explaining what is present in that image. That is, we call it as occlusion map. Occlusion map means we will mask one, divide your entire image into small tiles, and we will mask other parts, and we will show or we will check the prominence of each tile to show that, for example, whether that particular tile contains cat or whether this particular tile contains dog. And it is then represented using different colors like blue and red. Blue stands for strong presence and red is weak. And the image F and L are again GradCam outputs using another network called ResNet. Okay, anyway, we will see how this work. I have only show what is the output of GradCam. Instead of just saying that this contains cat and dog, the output is highlighting which portion shows cat, which portion shows dog. That is what we just saw it. And now let us the technical part, how it is actually working. So this is the network architecture that is taken from this paper. There's a GradCam visual explanation from Deep Networks. Selvaraju, he is the one who proposed this model. So what is actually doing here is, we have inputs. I will explain this with the help of case of a medical case. We have a set of chest X-ray, and we want to predict whether this chest X-ray is a normal or chest X-ray comes from a pneumonia patient or a COVID patient. So what we are doing here is, we will just like a normal AI, how it predicts. Y indicates the score, whether it is a normal. Y normal indicates. Y pneumonia indicates whether this belongs to a pneumonia patient. Y COVID represents the score. It belongs to a COVID patient. Next, what we are doing here is, if we are interested only in the pneumonia case, we want to give an explanation that, for example, suppose this X-ray belongs to a pneumonia patient, and the model predicts that this belongs to a pneumonia patient. So we need to say, or we need to know how this belongs to a pneumonia patient. And for that, we need an output like this. Because of this particular region, this highlighted region, that X-ray belongs to a pneumonia patient. So we can highlight this so the doctor can easily recognize there is something present in this region. And that is why this image is contributes to pneumonia. So we will take 3 different scores. And if you're interested only in pneumonia, what we are doing here is, we will find in the, in this model, you have a CNN model we are basically using for prediction. So in the CNN model, you have so many convolution layers are there, so many feature maps are there. So before the prediction, just before the prediction or the final fully connection layer, we will have a last convolution layer, last feature map. We will compute the gradient of your prediction with respect to that feature map for each of the case. And if you are interested only in pneumonia, we will make the gradient of the other 2 cases 0. Y normal and Y COVID, we will make it as 0. And we will allow only the gradient of pneumonia to propagate backwards. Then with respect to the last convolution layer, we will compute a score, the importance of weight of each channel. In this figure, you can see that there are so many channels associated with the last convolution layer. So for each channel, we will compute an importance using this equation. Alpha case is the importance of the kth channel. Then multiply that importance with that feature activation map and pass this through a ReLU layer. ReLU means, rectified linear unit. And this output is called LC grad chem. That will be a matrix similar to the size of your image. So the output of this equation will be a matrix highlighting which features or which region of the image contributes to pneumonia. And you are multiplying your original image, that is this input, with your grad chem image to get your final output. So this is the way the grad chem works. Next, another model is SHAP. SHAP is, shapely adaptive explanation. That is a full form of SHAP. It is actually working on a concept of a cooperative gaming theory, which means how much each feature contribute to a prediction. If 5 or 6 members are involved in playing a game, what is the contribution of each player in the winning chance of the game? We will simply take the case. AI predicts the probability of a heart disease based on 3 inputs. We are providing age as input, blood pressure, cholesterol. These are the 3 inputs we are providing. So these are the values also listed here: 65, 180, 280. So based on these 3 inputs, AI predicts the probability of heart disease as 90%. And we want to know how much of this 90% prediction came from age, how much came from blood pressure, how much came from cholesterol. Definitely, a patient like anyone may ask, why heart attack or heart disease caused? Is it due to my cholesterol? Is it due to your blood pressure, or is it due to the age? So we have to find the contribution from each parameter. So, if you're taking age alone, the risk may be only X%. But if you take blood pressure and age, the contribution of the age may increase. I mean, it may be by another Y%. So depending upon the combination of different features, the contribution made by that feature will be different. So how can we compute what is the exact contribution of each feature in causing that disease? So for that, we need to take different combinations or different orders also. For example, we are starting with nothing. So without any input, there is a 20% probability that that person will have a heart disease. That's the baseline probability. We take it as 20%. Then you provide age. So that model predicts there is a 40% chance of heart disease. So the contribution of your age is from 20 to 40, that is 20%. Then you add blood pressure. That prediction becomes 70%, which means from the prediction, from the 40%, it becomes 70%. So what is the contribution of BP? It is 30%. Then you add cholesterol. The total prediction is 90%. So from 70, it becomes 90. So the contribution of cholesterol is 20%. And here we made a contribution of age 20%. In the another order we are taking, here we have started with age, but here in the order 2, the baseline is 20%. We are starting with cholesterol. So now the prediction becomes 35%. Then we add age, prediction becomes 55%. So again, the contribution of the age here is 20. And you are taking order 3. You are starting with blood pressure. And you are adding your age at last. Here the contribution is 15%. So in these 3 different orders, what are the contributions of age? In the first case, it is 20. Second case, it is 20. Third case, it is 50. So the contribution of each feature is getting changed depending upon the order we are taking. So how can you combine all this? For this, we have to find a single value called tap value using this equation. This equation, as you see, is quite complicated, but is when you analyze this, it is very simple. Here, S means the subset of the features available. So initially, we are taking that we have no set of features. So S means this is nil. S means it is nil, that is 0. So in this equation, if you take the first case, this becomes 0, this becomes 0. And what is capital F? Capital F is the complete set of features. Here we are taking F is equal to 3, which means you have age, cholesterol, and BP. So this F will be 3. And initially S is equal to 0. So substitute in this, you will get this factorial value as 1 by 3 here. And what is this part? This part is initially S is equal to nil. And you are finding the union S union I. I is the first feature you are adding. First feature you are adding is H. So that is F of nil union A is F of A. Minus F of S means F of nil. So that is the first term. Second is initially you have added blood pressure B. So S is B. That is initially you have B. Union H. So you have F of AB. Minus F of S means that is a blood pressure. And here S becomes 1 at this point because you have already one existing feature. F remains 3 itself. So you will get 1 by 6 as the value. Similarly, initially you have cholesterol. Then in the last case, initially you have blood pressure and cholesterol. You are adding age at last. So you'll get 4 different terms. Then you will add all these 3 and this constant indicates the weight associated with that prediction. And finally, you will get a single value for this. Single value for that age. So this value will represent what is the contribution of each feature in causing that disease. This is the way SHAP works. So this can be, this is applicable in image situations also. This is just the case of a very simple case. And the next one is live. That is the explanation. I mean, full form is local interpretable model agnostic explanation. So this is unlike the previous cases. This works in a different way. Here we are approximating our complex model with a simple and a local model. And you know this works with every machine learning. Any machine learning model you can use here for making the prediction, and that prediction will be explained. You can see here. This case, you have an original image. This is your original image. The frog carrying something. It's a funny image. So what we are the prediction made by our complex model, which means this is the image of a tree frog. So the model predicted this is the image of a tree frog with 54% probability. So what we are doing here is we are making or we are first creating. Suppose for this is, if this is your input image, you will create so many random images from this just by masking different portions of this image. You have one input here, you have another input, you have a third input here. So you will generate so many random images by just perturb instances. You are making this, and you will design a simple model to predict this particular input as tree frog. For example, this is just like a linear regression. Your actual model is a curved one, that is a complicated model. Then for this input, you will generate so many random images. These black dots are the perturbed instances or random images generated from your original input. And you will, the straight line is the simple model that you have generated. So in this equation, F is your original model and G is your simple model. So F has make a prediction that this is frog, and G is trying to make an explanation to the prediction made by F. So in order to make the explanation, we are creating a simple model, and this simple model will tell you why this is frog. So out of these three instances, this is one simple model, this is another simple model, this is another prediction made by the simple model. So the highest probability is 0.85. So we are taking this as your explanation. It is because of this part. This is the unmasked part of that image. So it is because of this part, this image is considered to be frog. So the lime made a simple model and provides an explanation that why this is frog. It is because of this head portion. This image is predicted to be frog. Okay. So for that, this is the objective function used. You are minimizing the prediction differences between your original model and the simple model subject to a kernel that you are using here. I am not going to the details of that. And this is one parameter, that's a penalty parameter that you're using. Okay, so anyway, this is the way this line works. And we will, I think we can wind up this session after discussing a case study for this explainable AI. This is a case study that I have included from another paper called Explainable AI Model for Multiple Lung Disease, published in 2024. This is the paper for diagnosing COVID-19, pneumonia, and tuberculosis based on X-ray images. And this works based on the DenseNet 201 as the backbone. And here they have used the AI techniques such as SHAP, LIME, GradCam, and GradCam++. And this is the workflow of that, how they did it. Initially, they have created the data set. Data acquisition was that the lung disease data set they have used around 10,000 images and 4 types: normal, pneumonia, COVID-19, and tuberculosis. So first they have done data augmentation, like rescaling the image to the size 224 by 224. Then they have done some rotation, shifting widthwise and heightwise, shearing, zooming your image, horizontal flipping, fill mode. That are the data augmentations. Then some data preprocessing, like denoising, contrast preprocessing, gamma correction. Then splitting the data into train, validation, and test. And you have used DenseNet 201 model. So this is that block explaining. And you have used, they have used other models like EfficientNet B0, Inception V3, LayNet, just for comparison purpose. And the result of the prediction of this model is given to different XAI like GradCam, SHAP, LIME, etc. for interpretation. Okay, as I told you, this is the splitting. They have done it for, this was the original data set. And this is the data set after augmentation. So you must note that in original data set, this is the distribution of images for 4 different categories for validation. And even after augmentation, the number is still same in validation, because augmentation is applicable only for training. You compare these two. This is after augmentation. You have here 4,866. Here only 1,506. So almost 3 times the image size has been increased after augmentation. Also the testing data set is also still same. We are not doing any kind of augmentation in testing and validation. After splitting, we are doing augmentation on this 80% training data set. And then the parameters used for data augmentation, as I told you, have used shearing, how much 20%, zooming 20%, flipping we have done it, and shifting by 10%, and rescaling, you're dividing it by 255 to rescale these pixel values to 0 to 1, and rotation 20%. Then we have in the pre-processing stage, you have used autoencoder for denoising. So autoencoder means for every input, you will generate noisy inputs. If X is your original, sorry, if X, given X is your input, which is a noisy one, noisy image that you are adding some noisy random distributions to create X cap. That is your noisy image data. Then this encoder will compress this input to some features. Like if X cap is your noisy image that you have created, Z is the feature representation, latent feature representation learned by that encoder. Then with the help of this learned feature Z, it makes a prediction, or it will regenerate your original image. So what we are actually doing here is we are training our model to remove or regenerate your original image from a noisy image. So what they did is, initially you have an original image, you will randomly add noise to that image, you will create several copies. And from these noisy images, you are learning the latent features or the required features of your original image. So once you have those learned features, you can get your original image even if your input is noisy. And for that, you are using a loss function, just like squared error function. Your original image and the predicted image difference is kept to be minimum. And next is contrast improvement. That is a contrast limited adaptive histogram equalization. This is just like an adaptive histogram equalization, but you are using a you're clipping the histogram peak based on a clip count. So the contrast is limited. After clipping, you are redistributing your histogram bins and just apply the equalization. That is contrast limited adaptive histogram equalization. And gamma correction means you have your input image IN, just taking an exponent on each pixel, multiply with a constant. So depending upon the exponent gamma, it can brighten your image or it can darken your image. Gamma is less than 1 means brightens, gamma is greater than 1 means it darkens the image. So this is the preprocessed image. You have a normal image here, and this is the denoisy one. So you cannot feel much different between these two. And this is contrast limited adaptive histogram equalized image, and this is the gamma corrected image. Here the gamma is kept to be less than 1. And this is just the architecture of their proposed architecture. Here you provided your input, and initially you have a convolution layer with the kernels of size 7 by 7, and the stride is 2. Then you have a max pooling layer, and this is followed by a dense block layer. Dense block layer means, unlike a normal convolution layer, in normal convolution layer, the output of each layer is connected as the input of the next layer. But in dense block layer, the output of all previous blocks will be fed to the next layer. That is why it is called dense block layer. So you have a dense block layer. Then again, you have another convolution layer, again dense block 2, again translation, dense block 3, translation layer, dense block 4. And finally, this is connected to the classification layer. We'll use global average pooling and a softmax, which makes the classification into 4 types. Here we have used, in addition to GradCam, map, and Lime, they have used another technique called GradCam plus. It is nothing but we have discussed this equation, ReLU equation, to create the feature map. Here, this equation is modified to include one more term, which is subtracted from the first term. So, what is the significance of this term is that you are taking one feature AK, I mean one activation map, and you are subtracting the contribution of all other activation maps from this particular activation map. So if one activation map, say AK, is much prominent, then even after subtraction, this total value will be positive. That you can identify that. Otherwise, it will be negative. So in order to identify the contribution of each feature, one feature map with the combined contribution of all other feature maps. That is why we are using this. Okay, and this is that GradCam heat map and GradCam plus heat map for a normal patient, and this is for a pneumonia patient. GradCam and GradCam plus feature map is important. And this is the that one using Lime. Why this is called a pneumonia image is due to the portions that are highlighted that comes within this region. And this is that using SHAP. The different regions are highlighted in different colors, as I told you. COVID-19 and pneumonia is due to this region, and COVID-19 is to this region. Okay. And this is the final slide. I think we can stop it here. This is a concept where integrating explainable AI in federated learning. We have already seen what is explainable AI, what is federated learning. By integrating these two approaches, it's nothing novel. Federated learning means the learning happens inside every local server. So we are integrating that explainable AI into the final model to explain how it happened. Or even you can, if you want, you can move that explainable AI to local server. Okay, actually, I think if you start moving to the next topic, it will consume more time. I had planned for another topic also, data strategy, which means how you handle the data, especially in biomedical data, what type of augmentations you have to do, and what type of just skip this slide and just to show you. Actually, there are 7 stage data pipeline, and when you handle the data, or when you there are several issues like class imbalance in biomedical data sets. So at that time, what will we do? Which are the different performance measures you have to concentrate on class imbalance issues and different possibilities of data augmentations, especially for biomedical data, and how do you split your data in case of biomedical validation and all. But if you started explaining this, I think it will be much, it will take much time. Okay, so I think the coordinator, Christina ma'am and Vinod sir are available here. So we can stop here.
Okay, sir.
Thank you, sir, for delivering such an insightful and engaging session. Your valuable knowledge, practical insight, and expertise have greatly enhanced our understanding of the topic. We sincerely appreciate the time and effort you have taken to share your experience with us. Your session has been truly informative and inspiring, and we are confident that the knowledge gained today will be beneficial to all of us. Now, I would like to invite the participants to share their feedback, comments, or questions regarding today's session. So, we shall now present token of gratitude to our esteemed resource person in appreciation of his valuable time and insightful session. On, on, on behalf of the Department of Electronics and Communication Engineering, I extend our heartfelt gratitude to you for your valuable presence and contribution. Thank you, sir, once again. Wishing you all the best and continuous success in your future journey.
Okay, thank you. Second, thank you all.
With this, we conclude today's section of the 6-day International Faculty Development Program on Smart Biomedical and Sustainable Electronic System, AI, IoT, and Green Technologies. I would like to extend our heartfelt appreciation to all the resource persons for sharing their expertise and to all the participants for your active engagement and support. We hope today's session have been informative and enriching. We eagerly look forward to your participation in tomorrow's session. Once again, thank you all.